NASA spent billions. Amateur astronomers spent thousands. Guess who captured better images of 3IATLAS? This isn't about conspiracy, it's about asking why. On November 19th, 2025, NASA finally broke their silence. After 47 days of waiting, after weeks of speculation, after amateur observers around the world had already documented the comet's complex jet structure, NASA held a press conference to reveal what their fleet of spacecraft had captured during 3IATLAS's historic journey through our solar system. The anticipation was enormous. The Mars Reconnaissance Orbiter had photographed the interstellar visitor from just 29 million kilometers away. The high-rise camera aboard that orbiter cost $720 million and was designed to capture surface details on Mars with extraordinary precision. It represents some of humanity's finest optical engineering, capable of resolving features just 30 centimeters across from orbit. When NASA finally showed those images, something felt wrong. The comet appeared as a blurred streak. Motion smear, they explained. Spacecraft jitter. Technical limitations. Understandable, perhaps, for such a challenging target. But here's what makes this story remarkable. While NASA's billion-dollar instruments struggled to produce clear images, amateur astronomers using equipment costing a few $1,000s captured stunning photographs showing intricate jet structures, massive anti-tails extending nearly 1 million kilometers, geometric patterns in the coma, and details that simply weren't visible in NASA's official release. Ray's astrophotography in November captured images showing at least 6 distinct directional jets. Gianluca Massi at the Virtual Telescope Project documented a 950,000-kilometer anti-tail pointing directly toward the Sunday. Satoru Murata, using a standard Celestron telescope verified by the International Comet Quarterly, produced images revealing asymmetric emissions and forward-projected beams that looked almost architectural in their precision. These weren't lucky shots. These were systematic observations using publicly available processing software like PixInsight, conducted by skilled observers who understood their equipment and knew how to extract every bit of information from their data. And they did it faster, clearer, and with more detail than NASA's official presentation. This raises uncomfortable questions, not about conspiracies or cover-ups, but about institutional priorities, bureaucratic delays, and whether the world's premier space agency is operating as effectively as it should when faced with a once-in-a-generation scientific opportunity. If you watched our first video covering NASA's official update, you know we said that the next step would be a deeper analysis. So that's what we're doing here. No dramatics, just a closer look at the questions the space community has been raising. Since the November 19th presentation, a lot of astronomers, researchers, and long-time observers expected clarity from NASA's release. Instead, many walked away with more questions than answers. Today's video isn't about guessing or sensationalizing. It's about understanding why the update felt incomplete, what information was missing, and what the data actually suggests when you look past the surface. If you want to keep following this investigation as new observations come in, feel free to subscribe so you don't miss the next stages, especially with the December observation window approaching. Now, let's get into what NASA showed us and what they didn't. Let's start with what we know for certain. Before we explore what went wrong, let's establish the baseline. What did NASA actually confirm during their November 19th presentation? 3IATLAS is definitively a comet, not an asteroid, not something ambiguous, an active comet with all the expected characteristics. It has a nucleus composed of ice and rock. It has a coma, the glowing envelope of gas and dust that forms when solar radiation heats the surface and causes volatile materials to sublimate. Spectroscopic observations detected water vapor, carbon dioxide, hydrogen cyanide, and nickel in the coma. All chemical signatures consistent with cometary composition. The trajectory is precisely calculated. 3IATLAS entered our solar system from the direction of Sagittarius, moving on a hyperbolic orbit that confirms its interstellar origin. The mathematics are unambiguous. This object came from another star system, passed through ours, and will leave again, never to return. Its velocity when discovered was approximately 61 kilometers per second relative to the Sunday. That's roughly 220,000 kilometers per hour. far too fast to be gravitationally bound to our solar system. Size estimates place the nucleus somewhere between 440 meters and 5.6 kilometers in diameter. That's a huge range, reflecting the difficulty of separating the bright nucleus from the surrounding coma. Later refinements suggest the nucleus is probably closer to the smaller end, perhaps under a kilometer in diameter, similar to 2I Borisov, the previous interstellar comet. Perihelion occurred on October 29, 2025, at approximately 1.36 astronomical units from the Sunday. That's about 203 million kilometers, placing the closest approach between Earth's orbit and Mars's orbit. During this period, Earth was on the opposite side of the Sun, blocking direct ground-based observation of the most active phase. The comet survived perihelion intact. Images captured on November 11th by David Jewett and Jane Liu using the Nordic Optical Telescope confirmed a single cohesive nucleus with no evidence of catastrophic fragmentation. This matters because the intense solar heating and tidal stresses during close approach often break apart weakly bound cometary nuclei. Activity increased substantially around perihelion, as expected. Brightness surged approximately five-fold in visible wavelengths between early October and early November. Jets became more pronounced. Outgassing rates climbed. All standard comet behavior amplified by proximity to the Sun's energy. The upcoming close approach to Earth will occur on December 19, 2025, at approximately 1.8 astronomical units. That's about 270 million kilometers completely safe, but close enough for excellent ground-based observations with professional and amateur telescopes. These facts are solid, confirmed by multiple independent observations, not subject to interpretation beyond normal scientific uncertainty about measurements. But around these facts swirl questions that NASA's presentation barely touched. In our previous videos, we explored the 12 documented anomalies that make 3IATLAS unusual among comets. We examined how its trajectory aligns within 5 degrees of the ecliptic plane, despite only a 0.2% probability for such alignment. We discussed the persistent anti-tail that appears across changing viewing geometries. We looked at the timing that brought it close to multiple planets, while hiding perihelion behind the Sun from Earth's view. We covered all of that before NASA's official update. And we expected NASA to address these unusual characteristics during their presentation, to explain them, to provide the detailed analysis that only their instruments and expertise could offer. Instead, what we got was a presentation that felt carefully managed to emphasize normalcy, natural comet, behaving as expected, nothing unusual, move along. But the astronomical community didn't move along, because the images NASA finally released, after 47 days of waiting, after promises of unprecedented clarity, after all that, anticipation those images raised more questions than they answered. And that's where our investigation truly begins. Let's walk through exactly what happened, day by day, and understand why the response from the astronomical community was so frustrated. July 1st, 2025. 3IATLAS is discovered by the Atlas Survey Telescope in Chile. Within hours, follow-up observations begin confirming its interstellar trajectory. The astronomy world ignites with excitement. Only the third interstellar visitor ever confirmed. Only the second active comet from beyond our solar system. Throughout July and August, observations accumulate. Hubble captures images on July 21st. Ground-based telescopes track the comet's evolution. Amateur networks begin coordinating observations. Everything proceeds normally, with data flowing into public databases as it's collected. October 2nd and 3rd, 2025, the critical moment, 3IATLAS passes within 29 million kilometers of Mars. Multiple spacecraft turn their instruments toward this rare visitor. NASA's Mars Reconnaissance Orbiter captures images with its high-rise camera. China's Tianwen-1 orbiter also photographs the comet. The European Space Agency's Trace Gas Orbiter and Mars Express add their observations. This is the closest any spacecraft will get to 3IATLAS, the optimal viewing geometry, the moment when the highest resolution images should reveal details about the nucleus structure, jet patterns, and coma dynamics that ground-based telescopes simply cannot resolve. And then, silence. October 4th, 2025. The United States government shutdown begins. Federal agencies including NASA face operational restrictions. Personnel are furloughed. Normal work grinds to a halt. But here's what makes the timeline interesting. China's Tianwen-1 images appeared online within days. Clear photographs showing the comet's coma structure, visible tail, general morphology. Not perfect images. The spacecraft wasn't designed for tracking fast-moving distant objects, but scientifically useful and immediately accessible. NASA's images remained locked away. October passes. The comet reaches perihelion on October 29th. Ground-based observations are impossible because the comet is directly behind the Sun from Earth's perspective. The Mars orbiter data becomes even more valuable because it captured the comet during the most scientifically interesting phase of its journey. The November arrives. The government shutdown continues through the first 2 weeks of the month. 3IATLAS emerges from behind the Sunday. Ground-based observations resume on October 31st. And here's where something remarkable happens. Amateur astronomers around the world begin capturing extraordinary images. November 8th, 2025. Michael Yeager, Gerald Riemann, and Eric Prosperi capture stacked images showing at least 7 distinct jets emanating from 3IATLAS. The images reveal jets pointing both toward and away from the Sunday. The spatial scale is enormous, extending out to 500,000 kilometers. November 9th, 2025. Frank Niebling and Michael Buchner produce a stacked, deep image, combining 5 exposures of 3 minutes each. The result is stunning. 2 anti-tail jets extending nearly 1,000,000 kilometers toward the Sunday. A longer collimated jet reaching 2.85 million kilometers away from the Sunday, tightly focused structures that appear to maintain their orientation despite the comet's known rotation. November 14th, 2025. Multiple sources report that NASA will release the high-rise images within days. The shutdown has ended. Processing can resume. The astronomical community prepares for the reveal. November 15th, 2025. Tirasak Phaluang in Thailand captures images using an amateur telescope with gradient filters. The 950,000 kilometer anti-tail is clearly visible. Geometric patterns in the coma are evident. November 16th, 2025. Satoru Murata produces images combining 24 exposures of 60 seconds each using a 0.2 meter Celestron telescope. The image is verified by the International Comet Quarterly. It shows multiple jets in various directions, including prominent sunward features and asymmetric coma structure. November 17th and 18th, 2025. More amateur images flood online platforms. Francois Kugel contributes high-quality observations. The Virtual Telescope Project hosts live streams. Ray's astrophotography continues documenting the complex jet evolution. By the time NASA holds its official presentation on November 19th, the global amateur astronomy community has already documented 3IATLAS's post-perihelion behavior in extraordinary detail. The complex jets, the persistent anti-tails, the geometric structures, the brightness variations. All of it visible in images taken with modest equipment by skilled observers who understand their instruments. November 19th, 2025, 3 p.m. Eastern Standard Time. NASA goes live with their official presentation. The stream begins with expected messaging, scientific opportunity, interstellar visitor, rare chance to study material from another star system, safety assurances, no threat to Earth. Closest approach will be 270 million kilometers away on December 19th. All perfectly reasonable. Then the images appear. The high-rise photograph shows a blur. A bright central region smeared across several pixels. Some general coma structure visible. The overall shape discernible. But the fine details, the jet structures, the nucleus morphology, the features that amateur images had been revealing for weeks, largely absent. NASA acknowledges the limitation immediately. Spacecraft jitter during exposure. Relative motion between the orbiter and the comet. Technical challenges of photographing a fast-moving target from another fast-moving platform. All technically accurate explanations. But the disappointment in the astronomy community was immediate and visceral. Dr. Theodore Carretta, planetary astronomer at Villanova University, would later note that spacecraft missions provide key observational advantages, different vantage points, specialized instruments, perspectives impossible from Earth. The implication was clear. Those advantages hadn't translated into superior results in this case. Avi Loeb, Harvard astrophysicist and head of the Galileo project, was more direct. In his Medium post published shortly after the briefing, he wrote, "In retrospect, these amateur astronomer images are far more exciting than the high-rise image shared by NASA's officials." He wasn't alone in that assessment. Across astronomy forums, social media platforms, and professional circles, the same question kept appearing. How did backyard observers with consumer-grade equipment produce better documentation than NASA's Mars Reconnaissance Orbiter? The Medium article titled "NASA's Disappointing Release by Earth Exists" laid out the comparison starkly. On one side, amateur observations showing excellent detail, clear geometric jets, structured zones, and 950,000 kilometer anti-tails. On the other side, NASA's $720 million orbiter producing what the article called point source only imagery. The criticism crystallized around several key points. First, the image quality itself. HiRISE is designed for precision. It routinely captures extraordinarily detailed images of Mars's surface from orbit. Its stabilization systems are sophisticated. Its targeting capabilities are proven. The fact that it struggled with 3IATLAS while amateur astronomers succeeded suggested either the observation parameters weren't optimally configured or something else went wrong that NASA wasn't fully explaining. Second, the timeline. 47 days from image capture to public release. Even accounting for the government shutdown, the images existed within NASA's systems for over 6 weeks before anyone outside the agency saw them. What analysis occurred during that time? Were scientists verifying unexpected features? Running comparisons with models? Checking for artifacts? Or was it simply bureaucratic slowness? Third, the contrast with other space agencies. China's Tianwen-1 released images within days. The European Space Agency provided regular updates. Amateur networks shared findings in real time. Only NASA, with arguably the most capable instruments, maintained extended silence. Fourth, the missing spectroscopic data. The James Webb Space Telescope observed 3IATLAS in August 2025. That's 3 months before the November 19th presentation. Spectroscopic data doesn't require months of processing, it's relatively straightforward to analyze. The community expected detailed chemical composition, isotopic ratios, volatile distribution, and coma structure analysis. None of that appeared in the presentation. The silence on JWST results was deafening. Fifth, the superficial treatment of anomalies. The anti-tail received brief mention with standard viewing geometry explanations. The rotation versus jet structure puzzle got glossed over. The nickel detection was acknowledged but not explored in depth. Each unusual characteristic was mentioned, labeled as within normal parameters, and the presentation moved on. The overall impression was of an institution more concerned with managing messaging than sharing science, more focused on emphasizing normalcy than acknowledging uncertainty, more invested in reassuring the public than engaging with the questions that made 3IATLAS genuinely interesting. Representative Anna Paulina Luna's letter to NASA, sent before the presentation, captured the frustration. She urged immediate data release, noting that this information is of great importance to advancing our understanding of interstellar visitors. The implication was clear. Delays weren't just bureaucratic inconveniences, they were impeding scientific progress. Loeb put it more bluntly, science should have been prioritized over bureaucracy. The truth about the nature of 3IATLAS will be revealed by the sharing of data, not by the storyline of gatekeepers. Whether that's entirely fair to NASA is debatable. Large government agencies operate under constraints that amateur astronomers don't face. Legal requirements, security protocols, multi-level approval processes, coordination across different missions and institutions. These aren't trivial considerations, but perception matters in science. And the perception created by the November 19th presentation was that NASA had underdelivered, that the world's premier space agency, with resources amateur observers can only dream of, had been outperformed by dedicated individuals with modest telescopes and processing software. That perception drove the response, not just from critics like Loeb, but from the broader astronomy community that had been waiting eagerly for insights only NASA's instruments could provide. The disappointment was real. The questions were legitimate, and as we dig into what NASA didn't address, you'll see exactly why those questions matter so much. Let's start with the most visible disappointment: the high-rise images themselves. The high-resolution imaging science experiment camera aboard the Mars Reconnaissance Orbiter represents some of humanity's finest optical engineering. Launched in 2005, it has been capturing extraordinary images of Mars for nearly 20 years. Its primary mission is mapping potential landing sites and studying Martian surface geology in unprecedented detail. The specifications are impressive. At its lowest altitude, roughly 300 kilometers above Mars's surface, HiRISE can resolve features as small as 30 centimeters across. That's about the size of a dinner plate, visible from space. The camera uses a half-meter primary mirror large for a spacecraft instrument paired with sophisticated charge-coupled device detectors that capture images in 3 color bands. The instrument was built by Ball Aerospace, designed specifically for precision work. Its pointing system can track targets with high accuracy. Its image processing pipeline can handle the complex task of capturing sharp photographs while the spacecraft moves at thousands of kilometers per hour. This is not amateur equipment. This is a $720 million orbital platform that has produced some of the most detailed images of another planet ever captured. So when NASA announced that HiRISE had photographed 3IATLAS from just 29 million kilometers away, roughly 10 times closer than Earth-based telescopes could observe, the astronomical community expected something extraordinary. The spatial resolution should have been approximately 30 kilometers per pixel at that distance, about 3 times better than the best publicly available Hubble image from July 21st. The expectations were high, but justified. This was humanity's best opportunity to see an interstellar object up close. Mars's fortuitous position during 3I-Atlas's perihelion passage created a viewing geometry that wouldn't be replicated. If HiRISE couldn't capture good images, nothing would. Then the images appeared during the November 19th presentation. The comet was visible as a bright smeared streak across several pixels. The general coma structure was discernible. You could tell this was an active comet with an extended dust envelope. But the fine details, the jet structures amateur astronomers had been documenting for weeks, the potential nucleus morphology, the specific features that might distinguish this interstellar visitor from solar system comets, those details were largely absent. NASA's explanation was straightforward. Spacecraft jitter and relative motion during the exposure period created blur. The orbiter moves, the comet moves. The combination during a 3.2-second exposure smeared the light across multiple pixels. Shane Byrne, HiRISE principal investigator at the University of Arizona, acknowledged the challenge. Observations of interstellar objects are still rare enough that we learn something new on every occasion. The phrasing was diplomatic, but told you everything you needed to know. This hadn't gone as planned, but here's what makes this explanation unsatisfying to many observers. HiRISE photographs fast-moving targets regularly. Mars's surface features may not move, but the spacecraft certainly does, orbiting at roughly 3.4 kilometers per second. The camera compensates for this motion routinely, using sophisticated timing and tracking algorithms to freeze apparent motion during exposure. The instrument has photographed Martian dust devils, transient atmospheric features that move and evolve. It has captured images of avalanches in progress on Martian cliffs. It has tracked seasonal changes, documented new impact craters, and monitored dynamic surface processes. Motion isn't new to HiRISE. So what went wrong with 3I-Atlas specifically? Several possibilities exist, none of them particularly satisfying. First possibility: the observation parameters weren't optimally configured. Exposure time, tracking speed, and pointing accuracy all affect image sharpness. If the team didn't have perfect information about 3I-Atlas's position and velocity, the tracking might have been slightly off. A small error in predicted position translates to significant blur when photographing an object 29 million kilometers away. but that seems unlikely. The Minor Planet Center continuously updates trajectory information. NASA's Jet Propulsion Laboratory maintains precise ephemerides. By October 2nd, 3IATLAS had been observed for 3 months. Its trajectory was well constrained. The uncertainty in position shouldn't have been large enough to cause the observed smear. Second possibility, the exposure time was too long. At 3.2 seconds, the exposure duration gave both spacecraft motion and any comet motion time to blur the image. A shorter exposure might have frozen the motion better, though at the cost of collecting less light and potentially producing a noisier image. But HiRISE engineers know their instrument. They would have calculated the optimal exposure time based on the comet's brightness and their desired signal-to-noise ratio. If they chose 3.2 seconds, presumably that represented their best judgment about the trade-off between sharpness and sensitivity. Third possibility, the pointing system experienced unexpected drift during exposure. Spacecraft aren't perfectly stable platforms. Even with reaction wheels and gyroscopes, maintaining orientation, tiny variations occur. If the Mars Reconnaissance Orbiter experienced more jitter than usual during those critical seconds, it could have degraded image quality beyond what was anticipated. This explanation has the virtue of being unpredictable and beyond the team's control. But it raises the question of why HiRISE's stabilization systems, which normally compensate for spacecraft motion effectively, failed to do so in this case. Fourth possibility, the comet itself was moving in unexpected ways. If 3IATLAS's trajectory had subtle perturbations from outgassing the non-gravitational acceleration that comets experience when jets fire asymmetrically, the position during exposure might not have matched predictions perfectly. But the non-gravitational acceleration of 3IATLAS was measured and characterized. Its magnitude wasn't dramatically large. Any deviation from predicted position should have been minor, probably. Not enough to cause the level of blur visible in the released images. Fifth possibility, and perhaps most troubling, the images NASA released weren't the best ones captured. Perhaps other exposures with different parameters were taken. Perhaps some came out sharper, but for institutional or communication reasons, NASA chose to present these particular frames during the public briefing. This seems unlikely. Why would NASA deliberately show worse images? But it's the explanation that circulates in more skeptical corners of the astronomy community. The thinking goes, maybe better images exist, showing features NASA isn't ready to discuss publicly yet. Maybe the detailed structures visible in amateur photographs appear even more clearly in classified observations, and releasing those would spark uncomfortable questions. For what it's worth, I don't find this explanation compelling. NASA has strong incentives to share their best science. Their funding depends on demonstrating value to taxpayers. Their scientific credibility requires transparency. Deliberately withholding good images while showing poor ones would be bizarre institutional behavior. But the fact that some observers even consider this possibility tells you how much disappointment the blurred HiRISE images generated. The more prosaic explanation is probably closest to the truth. Photographing a fast-moving comet from a spacecraft orbiting another planet is genuinely difficult. The combination of relative motions, timing challenges, and operational constraints made this observation harder than anticipated. The HiRISE team did their best with the information and tools available. Sometimes in science, despite excellent planning and capable instruments, the data doesn't come out as clearly as hoped. That's not conspiracy, that's just reality. Science is hard. Space is unforgiving. Not every observation succeeds perfectly, but accepting that explanation doesn't erase the contrast with amateur observations. Because while HiRISE struggled with motion blur from a $720 million orbital platform, observers on Earth using equipment costing a tiny fraction of that successfully captured images showing tightly collimated jets extending millions of kilometers, complex multi-jet structures with at least 7 distinct streams, massive anti-tails pointing toward the sun across distances equivalent to 6 times the Earth-Moon separation, geometric patterns in the coma that appear structured rather than chaotic, brightness variations across different regions suggesting asymmetric activity, color differences indicating varying composition in different jets, How did they do it? What techniques did amateur astronomers use that apparently worked better than NASA's approach? The answer lies in methodology. Amateur astrophotographers don't take single long exposures of comets. They take many shorter exposures and combine them through a process called stacking. Rays astrophotography, for example, stacked multiple frames using PixInsight software. This technique averages out random noise while preserving true signal. It also allows for tracking adjustments between frames, compensating for motion more effectively than a single long exposure. The processing matters enormously. Modern astronomical image processing software like PixInsight, MaximDL, and others provide sophisticated tools for aligning images, removing artifacts, enhancing contrast, and extracting maximum information from raw data. Amateur observers have decades of collective experience refining these techniques. They share processing methods openly. They compete to produce the best possible images. The community continuously improves its capabilities. These observers also have a crucial advantage. They can wait for optimal conditions. If seeing is poor one night, they try again the next night. If the comet's position isn't ideal, they wait for better geometry. They're not constrained by spacecraft, orbits, mission timelines, or operational windows. Patience and persistence replace the advantages of proximity. The result is that skilled amateur astrophotographers working with modest equipment telescopes with apertures between 8 and 16 inches, commercially available CCD cameras, standard processing software can produce images that rival or exceed what some professional instruments capture under non-optimal conditions. This isn't new. Amateur contributions to astronomy have been growing for decades. As technology improves and costs decrease, the gap between professional and amateur capabilities shrinks. In some domains, like supernova detection, variable star monitoring, and yes, comet observation, amateurs routinely do work that once required professional resources. But the 3IATLAS case starkly illustrated this shift. When images from backyard telescopes showed details missing from NASA's Mars orbiter photographs, it forced an uncomfortable reckoning with questions about resource allocation, institutional effectiveness, and whether the world's most capable space agency is operating at the level the public expects. Those questions don't have easy answers. NASA does extraordinary work across dozens of missions. One disappointing image release doesn't erase that. But the contrast between expectation and delivery, between capability and result, between what $720 million should accomplish and what it actually produced, that contrast lingers. And it shapes how we interpret everything else about NASA's 3IATLAS presentation. When the highest resolution images disappoint, when the data you waited 47 days to see doesn't provide the insights you expected, it makes you more skeptical of the other conclusions presented. It makes you wonder what else might not be quite as definitive as the official narrative suggests. Which brings us to the next major gap, the jet structure that doesn't make physical sense. Given what we know about the comet's rotation, now we arrive at one of the most technically puzzling aspects of 3IATLAS, jets that appear to defy basic rotational physics. Back in July and August 2025, astronomers measured the comet's rotation period through photometry, monitoring how its brightness changed over time. As an irregularly shaped nucleus rotates, different faces reflect different amounts of sunlight toward observers. This creates a periodic dimming and brightening pattern. By analyzing this light curve, researchers calculated that 3IATLAS rotates approximately every 16.16 hours. This measurement wasn't crude guesswork. Multiple independent observations confirmed the period. The rotation was real, well-constrained, and unremarkable. 16 hours falls comfortably within normal ranges for cometary nuclei. Some comets spin in just a few hours. Others take days. 16 hours is typical. For comparison, think about Earth's rotation. Our planet spins once every 24 hours. If you're standing at the equator, you're moving eastward at roughly 1,670 kilometers per hour due to Earth's rotation. You don't feel it because you're moving with everything around you, but from space, that rotation is obvious. Now imagine Earth had jets of gas shooting out from specific locations on its surface. As Earth rotated, those jets would sweep through space like the beam of a lighthouse. Over the course of a day, each jet would trace a complete circle. If the jets fired continuously for a week, the pattern they drew in space would look like a spiral or helix, with the rotation clearly visible in the structure. This is basic rotational physics. If you have a spinning object emitting directed streams of material, those streams spread out in patterns that reveal the rotation. It's unavoidable. The rotation carries the emission source through different orientations, and the ejected material preserves that motion in its distribution through space. Now let's apply this to 3IATLAS. The comet nucleus rotates every 16.16 hours. Jets of gas and dust erupt from specific locations on the surface, probably regions where volatile ices are exposed to sunlight. As these ices sublimate, they release gas at thermal velocities. For a comet at 3IATLAS's distance from the Sun during early November, roughly 1.4 astronomical units, the expected outflow velocity is approximately 400 meters per second. 400 meters per second is the rough sound speed of gas at these conditions. It's not particularly fast by rocket standards, only 1440 kilometers per hour. But for cometary outgassing, it's typical. The gas molecules sublimate, gain thermal energy from solar heating, and stream away from the nucleus at velocities determined by temperature and molecular weight. At 400 meters per second, material travels 1.4 million kilometers in 1 hour, or put differently, 23.26 million kilometers in 16.16 hours, one complete rotation period of the nucleus. Now here's where the physics creates a problem. If a jet fires continuously from a specific location on the rotating nucleus, the material ejected early in the rotation period travels outward while the nucleus spins. By the time the nucleus completes one rotation, material is distributed along a curved arc roughly 23.3 million kilometers long. If the jet continues firing over multiple rotation periods, say, over the course of a week, the material spreads even more. The jet takes on a spiral or corkscrew pattern, with successive rotations adding to the structure. The overall shape resembles cotton candy being spun on a rotating stick. There's no way to avoid this geometry. The rotation inevitably smears directional jets into broad spiral patterns. This is what astronomers routinely observe in active comets. When high-resolution images capture jet structures, they show curves, spirals, and arcs that directly reveal the nucleus rotation. You can sometimes measure rotation periods just by looking at jet morphology. The spacing between successive spiral arms tells you how fast the nucleus spins. Now look at the post-perihelion images of 3IATLAS captured by amateur astronomers. November 8, 2025. Jaeger, Riemann, and Prosperi capture images showing jets extending approximately 500,000 kilometers. November 9th, Niebling and Buchner's stacked image reveals jets reaching 950,000 kilometers sunward and 2.85 million kilometers away from the Sunday. November 16th, Satoru Murata documents jets that appear tightly collimated across millions of kilometers. These jets look straight, not curved, not spiral, not smeared into the broad arcs you'd expect from weeks of continuous emission from a rotating nucleus. They look almost like beams, maintaining their orientation across spatial scales that should show obvious rotational effects. Think about the distances involved. 950,000 kilometers is more than twice the Earth-Moon distance. If material is traveling at 400 meters per second, it takes approximately 27.4 days to traverse that distance. During those 27.4 days, 3IATLAS completes approximately 40 rotation cycles, 40 complete rotations. The nucleus spins around 40 times while material travels from the source region out to the observed jet extent. How does that produce a straight jet rather than a massively smeared spiral structure? The physics appears contradictory. Either the jets aren't continuously emitted, or the rotation rate changed dramatically, or the material is traveling much faster than thermal velocities would predict, or we're not correctly interpreting what we're seeing in the images. Let's examine each possibility carefully. First possibility, intermittent emission. Perhaps the jets don't fire continuously. Maybe specific surface regions only release material when they face the sun at particular angles. Deep valleys surrounded by mountains might shadow ice deposits until the sun angle is just right. When those deposits briefly receive direct sunlight, They erupt vigorously. Then, as rotation carries them back into shadow, emission stops. This would create pulsating outflows. Instead of continuous streams, you'd get discrete puffs of material released during brief active periods each rotation. At 400 meters per second, material released during a short burst travels outward in a relatively narrow beam. The 16.16-hour rotation primarily affects when the next burst occurs, not the structure of material already ejected. If you think of it like a rotating sprinkler that only fires brief pulses rather than a continuous stream, you get straighter jets. Each pulse is essentially ballistic, following a straight trajectory determined by its initial velocity direction. The rotation affects the timing between pulses, but doesn't smear individual pulses into spirals. This mechanism is completely natural. Many solar system comets show diurnal activity variations, stronger outgassing when active regions face the sun, reduced activity when they rotate into darkness. The resulting jets can appear more collimated than continuous emission would produce. If this explains 3I-ATLAS's jets, it tells us the nucleus has distinct active regions rather than uniform sublimation. Probably irregular surface topology with localized ice deposits. Rotation brings these regions into sunlight rhythmically, creating structured pulsed emission rather than smooth continuous outgassing. But there's a timing problem with this explanation. For the pulsed emission model to work, each pulse needs to be relatively brief compared to the rotation period. If active regions erupt for several hours each rotation, you still get smearing. The emission must be concentrated into short bursts, maybe 1 or 2 hours out of every 16 to preserve the tight collimation observed. Is that plausible? It's not impossible, but it requires very specific geometry. The ice deposits need to be buried deep enough or surrounded by topography that blocks sunlight except during narrow windows. That's certainly possible on an irregularly shaped nucleus, but it's a relatively special configuration rather than generic behavior. Second possibility, rotation rate change. Maybe 3I-ATLAS rotated every 16.16 hours in July and August, when the photometric observations were made, but the rotation changed after perihelion. Asymmetric outgassing creates torque. If jets fire preferentially from one hemisphere or at angles that don't align with the rotation axis, they push the nucleus to spin faster or slower. Comet rotation rates aren't fixed. They evolve as the body loses mass and experiences non-gravitational torques. We've observed this in solar system comets. Some spin up dramatically as they approach the sunday, others slow down. The change depends on where the active regions are located relative to the rotation axis and how asymmetrically the jets fire. 3I-ATLAS might have experienced substantial torque during perihelion. If the rotation rate changed significantly, say, speeding up from 16 hours to 8 hours, or slowing down to 32 hours, that would alter how rotational smearing affects the jets. In an extreme case, if the rotation slowed dramatically, jets formed over several weeks would show less spiral structure than expected from the July-August rotation measurements. This explanation has appeal because it's entirely natural. No exotic physics required, just the well-understood mechanics of asymmetric mass loss creating angular momentum changes. But there's a problem with this too. Rotation. Changes from outgassing torque typically aren't dramatic enough to explain what we're seeing. To change rotation by a factor of 2 or 3 requires losing substantial mass asymmetrically. The amount of material 3I-ATLAS ejected during perihelion, while significant, roughly 5 billion tons according to some estimates, probably isn't enough to produce massive rotation changes unless the jets were extremely asymmetric and very far from the rotation axis. Moreover, we don't have recent rotation period measurements. The 16.16-hour value comes from July-August observations. Post-perihelion photometry would tell us whether rotation changed significantly. That data might exist in observations taken by professional and amateur networks during November, but it hasn't been publicly analysed and reported yet. We're operating somewhat blind about the current rotation state. Third possibility, higher ejection velocities. What if the material isn't travelling at thermal velocities of 400 meters per second? What if it's moving significantly faster? If jets are travelling at, say, 4 kilometers per second instead of 0.4 kilometers per second, the physics changes dramatically. Material covers the same distance in 1/10 the time. A 950,000 kilometer jet at 4 kilometers per second takes only 2.7 days to form instead of 27 days. During 2.7 days, 3IATLAS completes only about 4 rotations instead of 40. Less rotation means less smearing. Could jets move at 4 kilometers per second? In principle, yes, but only under specific conditions. Thermal sublimation at solar distances around 1 to 2 astronomical units typically produces velocities measured in hundreds of meters per second, not kilometers per second. To achieve supersonic velocities, you need either much higher temperatures, heating the gas, or some other acceleration mechanism. One possibility is that the jets we're seeing aren't primarily gas, but rather dust particles that were accelerated by the initial gas outflow. When gas streams off the nucleus, it can entrain dust particles and accelerate them. Depending on dust particle size and gas density, some dust can be pushed to velocities higher than the gas itself, but this effect typically produces velocities up to perhaps 1 kilometer per second, not 4 or 5. Another possibility is that subsurface pressure builds up before release, creating more energetic eruptions than simple surface sublimation. If volatile ices are buried beneath a dust mantle, solar heating can warm those ices without immediately releasing them. Pressure builds underneath the mantle until it ruptures, producing explosive outgassing at higher velocities than steady sublimation. This mechanism has been proposed for cometary outbursts and could potentially explain faster jet velocities, but there's no strong evidence that 3IATLAS experienced explosive eruptions rather than normal sublimation. The brightness evolution, while showing a surge, didn't show the dramatic sudden spikes characteristic of explosive events. The overall behavior looked relatively smooth, more consistent with gradually increasing sublimation as perihelion heating intensified. The higher velocity explanation also faces another challenge. Where's the energy coming from? Accelerating material to several kilometers per second requires substantial energy input. Solar radiation at 1 to 2 AU provides around 700 to 1400 watts per square meter. That's enough to sublimate surface ices at thermal velocities, but accelerating material to several times thermal velocity requires even more energy. Unless there's an internal heat source or some other energy reservoir, the physics doesn't obviously support sustained high-velocity jets. Fourth possibility, we're misinterpreting the images. Perhaps what look like tightly collimated jets aren't actually continuous streams of material at all. Several alternative interpretations exist. One is that we're seeing trails of discrete ejected fragments rather than gas streams. If perihelion heating caused the nucleus to shed chunks of material ranging from dust grains to meter-sized pieces, those fragments would follow ballistic trajectories outward. Each fragment travels in essentially a straight line, with its path determined by its ejection velocity and direction. Even though the nucleus rotates, once a fragment is ejected, it doesn't care about the rotation anymore. Its trajectory is set. If you have many fragments ejected at similar velocities and similar directions during brief active periods, they form a straight trail in space. The trail extends millions of kilometers, but it's not a continuous jet, it's a collection of ballistic projectiles, all moving along similar paths. From Earth, with limited resolution, this trail looks like a collimated jet. This interpretation implies that 3IATLAS experienced more fragmentation than NASA suggested. The November 11th images by Jewett and Liu showed an intact single nucleus, but those images couldn't resolve fragments smaller than tens or hundreds of kilometers. If the nucleus shed smaller pieces ranging from centimeters to tens of meters, those wouldn't be visible in available imagery, but could create extensive debris trails. Another interpretation possibility is optical effects. Perhaps the apparent jets are created by dust particle scattering properties rather than actual directed outflows. If dust particles with specific size distributions and compositions scatter sunlight preferentially in certain directions, they could create brightness enhancements that look like jets but don't correspond to actual material flows. This seems less likely for the anti-tail specifically, since seeing material apparently extending toward the sun requires more than just scattering effects. It requires material actually positioned between the nucleus and sunday. But for some of the other jet features, scattering geometry might contribute to their appearance. A fifth possibility, one that Avi Loeb has raised in multiple Medium articles, is technological. If the jets maintain their directionality because they're produced by controlled thrusters rather than natural sublimation, the straight collimation makes perfect sense. A spacecraft using jets for navigation or orientation control would naturally produce tightly directed streams that maintain their geometry regardless of the craft's rotation. The thermal velocity problem disappears in this interpretation because rocket thrusters can produce exhaust at whatever velocity their design specifies, typically kilometers per second for efficient propulsion systems. The rotation problem disappears because the thrust direction could be stabilized relative to inertial space rather than rotating with the body. I want to be clear, there is no evidence that 3IATLAS is technological. The compositional signatures match natural comets. The overall behavior is consistent with ice sublimation. Radio searches detected no narrowband transmissions. Every test applied so far indicates a natural object. But Loeb's point isn't that we should conclude 3IATLAS is artificial. His point is that we should honestly acknowledge when natural explanations face challenges. When jets extend millions of kilometers with tight collimation despite rotation that should smear them, that's genuinely puzzling. When the standard thermal sublimation model struggles to explain observed features, we should say so rather than glossing over the difficulty. The scientific approach is to lay out all possibilities, even uncomfortable ones, and then systematically test them with observations. The upcoming observations in December offer exactly that opportunity. Spectroscopic measurements of the jets can determine their velocity directly by measuring Doppler, shifts of molecular emission lines. If jets are moving at thermal velocities around 400 meters per second, that tells us one thing. If they're moving at several kilometers per second, that tells us something quite different. Similarly, better constraints on the current rotation period would help tremendously. If rotation has slowed dramatically since July-August, that partially explains the jet morphology. If rotation is unchanged, we need other explanations. The composition of the jets also matters. If spectroscopy shows they're primarily water vapor and carbon dioxide with trace cyanide and other typical cometary molecules, that supports natural sublimation. If the composition is anomalous in ways that don't match expected sublimation chemistry, that raises new questions. Mass flux measurements would be invaluable. How much material is actually flowing through these jets? If you integrate the mass loss rate over the time needed to form million-kilometer structures, do you get numbers consistent with the comet's size and sublimation capacity? Or does the required mass loss imply something unusual about the nucleus composition or structure? These are the questions that the November 19th NASA presentation should have addressed but didn't. Not with definitive answers necessarily, the data might not exist yet to answer them conclusively, but at least with acknowledgement that these are real puzzles requiring explanation. Instead, the official message was, jets exist, they're caused by active regions on the nucleus, this is normal comet behavior, moving on. That's not satisfying to anyone who looks closely at what the images actually show. The jets of 3IATLAS are not obviously normal. They display characteristics that sit uncomfortably with standard models. They might have natural explanations, probably do have natural explanations, but those explanations require more sophisticated physics than the simple picture NASA presented. The straight, collimation across million-kilometer scales, the persistence across changing viewing angles, the apparent lack of rotational smearing, the complex multi-jet structure with streams pointing in multiple directions, the massive anti-tail that maintains its geometry for weeks. All of these features individually have potential natural explanations, but collectively, they create a pattern that demands more careful analysis than NASA provided. And when you combine the jet puzzle with the other unexplained aspects, the nickel composition anomaly, the dramatic brightness surge, the trajectory alignment with the ecliptic, you start to see why some observers feel NASA's presentation missed the deeper story. Which brings us to the composition question, and specifically the nickel detection that got barely any attention during the briefing. On August 21st, 2025, the Very Large Telescope in Chile turned its high-resolution spectrograph toward 3IATLAS. The observation aim to characterize the comet's composition by identifying atomic and molecular emission lines in the light coming from its coma. Spectroscopy is one of astronomy's most powerful tools. When gas molecules or atoms are excited by sunlight, by collisions, by any energy input, they emit light at specific wavelengths determined by quantum mechanics. Each element and molecule has a unique spectral fingerprint. By splitting the comet's light into its constituent wavelengths and measuring which emission lines appear, astronomers can determine what chemical species exist in the coma. The August 21st VLT observations detected several expected features. Cyanide emission lines appeared clearly, confirming that hydrogen cyanide gas was present in significant quantities. This wasn't surprising. Cyanide is common in comets, formed in cold environments rich in carbon and nitrogen. Its presence tells you about formation conditions billions of years ago. But the VLT spectra also showed something less common: nickel emission lines. Nickel exists in cosmic materials. It's the 22nd most abundant element in the universe. It forms during stellar nucleosynthesis, primarily in the cores of massive stars that later explode as supernovae. The nickel produced in these explosions becomes part of the interstellar medium, eventually incorporating into the gas and dust clouds that collapse to form new stars and planetary systems. In our solar system, nickel appears in meteorites. Iron meteorites contain substantial nickel, often 5 to 20%, by mass-creating iron-nickel alloys with specific crystalline structures. Stony meteorites contain less nickel, but it's still present, typically less than 1%. The Earth's core is approximately 5% nickel, with most of our planet's nickel having sunk to the center during differentiation when Earth was molten. Comets form from materials that never experienced high temperatures or differentiation. They're primitive frozen samples of the conditions in the outer regions of the protoplanetary disk where they formed. Because they're primitive, their composition should reflect cosmic abundances modified only by volatility differences during formation. Nickel should be present in comets. The question isn't whether nickel exists in 3IATLAS, of course it does, but rather in what quantities and ratios relative to other elements. This is where things get interesting. The VLT detected nickel emission clearly enough to identify its spectral lines unambiguously. That requires a certain minimum concentration. Trace amounts wouldn't produce detectable emission. For the spectral lines to stand out above background noise, nickel atoms in the coma must exist in sufficient numbers to emit measurable light when excited by solar ultraviolet radiation. Detecting nickel emission in cometary spectra isn't unprecedented, but also isn't routine. Most cometary spectroscopic observations focus on molecules like water, carbon dioxide, cyanide, methane, ammonia, and simple carbon-bearing species. These molecules emit strongly and tell you most of what you need to know about comet composition and activity. Atomic metal emission like nickel, iron, sodium, and others requires different observational strategies and often isn't the primary focus. So when nickel shows up clearly in spectra, it's worth noting, it means nickel is present in concentrations high enough to produce observable emission when probably only a small fraction of the atoms are excited at any given moment. Here's what NASA said about the nickel during their November 19th presentation. 3IATLAS has been releasing more nickel than iron compared with solar system comets. Tom Statler, lead scientist for solar system small bodies, noted this was being investigated, but didn't elaborate. Here's what NASA didn't say. What exactly is the nickel to iron ratio? How does it compare quantitatively to known materials? Is the nickel distributed uniformly throughout the coma or concentrated in specific jets? Did the nickel signature change over time as different surface regions became active? What does the ratio of nickel to other elements, not just iron, tell us about formation conditions? These details matter enormously. Let me explain why. In cosmic abundance, iron significantly outnumbers nickel. For every nickel atom in the universe, there are roughly 17 iron atoms. This ratio reflects how nucleosynthesis works in stars. Iron is more readily produced than nickel in the nuclear processes that build heavy elements. Most natural materials reflect this abundance pattern. Meteorites, even iron meteorites rich in nickel, still contain more iron than nickel. A typical iron meteorite might be 12% nickel and 85% iron. with the remainder being other elements. That's nickel-rich by terrestrial standards, but still maintains iron dominance by a factor of 7. In terrestrial industrial contexts, we deliberately create nickel-rich alloys for specific applications. Stainless steel contains substantial chromium plus nickel for corrosion resistance. Some specialty alloys like Inconel are majority nickel, designed for extreme temperature and corrosion environments. These materials are engineered humans specifically concentrate nickel beyond natural ratios to achieve desired properties. When Avi Loeb notes that 3IATLAS's gas plume contains much more nickel than iron, as found in industrially produced nickel alloys, he's pointing out that the ratio appears inverted from cosmic norms. Instead of 17 iron atoms for every nickel atom, the observations suggest more nickel than iron. That's genuinely unusual, but how unusual? This is where the absence of detailed public data becomes frustrating. Without exact numbers, we can't assess how anomalous this really is. Is the nickel to iron ratio slightly inverted, say 1.2 nickel atoms for every iron atom? Or dramatically inverted 10 nickel atoms for every iron atom? The degree of anomaly matters for interpretation. Several natural processes could potentially create nickel enrichment. First, differential volatility during formation. Iron and nickel have similar but not identical chemical properties. In the cold outer regions of a protoplanetary disk, most iron and nickel would be in solid form, bound into mineral grains and ices. But subtle differences in how these elements behave chemically during condensation could lead to slight nickel enrichment in certain materials. If 3IATLAS formed from a reservoir that was mildly nickel enriched relative to cosmic abundances, that wouldn't be unprecedented. Second, preferential sublimation or release. Perhaps iron and nickel are present in normal ratios in the nucleus, but the processes that release them into the coma preferentially mobilize nickel. This seems less likely. Both elements would be bound in similar mineral forms and should sublimate or be released together, but complex surface chemistry might create some fractionation. Third, observational effects. The nickel detection comes from emission spectroscopy. For an atom to emit light, it must first be excited to a higher energy state, then relax back down, releasing a photon in the process. Different elements have different excitation requirements. Nickel might be more easily excited by solar ultraviolet radiation than iron under the specific conditions in 3IATLAS's coma. If so, the spectral intensity ratio wouldn't directly reflect the abundance ratio. This last possibility is important because it means we can't necessarily take the observed emission intensity ratio and directly interpret it as the abundance ratio without careful modelling. Spectroscopy is powerful but not always straightforward. Converting emission line intensities to abundances requires understanding excitation, conditions, ionization, states, temperature, density, and other environmental factors. Fourth, the nickel and iron might come from different source materials within the nucleus. If the nucleus is heterogeneous, composed of different types of ices and dust mixed together, perhaps some regions are iron-rich, while others are nickel-rich. If the currently active regions happen to be sampling nickel-rich material, the coma composition would reflect that, even though the bulk nucleus composition might be more typical. All of these are natural explanations that could potentially account for enhanced nickel. But without the detailed data, exact intensity measurements, how they convert to abundances given the excitation modelling, spatial distribution in the coma, time evolution, we can't evaluate which explanations actually fit. There's also the comparison to other elements beyond just iron. Loeb mentions that the nickel to cyanide ratio is orders of magnitude larger than in all known comets. Again, without seeing the actual numbers, it's hard to assess this claim fully, but if true, it suggests the nickel abundance is high relative to multiple different cometary components, not just iron. That makes simple explanations less satisfying. The VLT has the data. Those observations happened in August. By November 19th, 3.5 months had passed. Spectroscopic data analysis doesn't require months of processing for basic results. You can extract emission line intensities, identify features, and measure ratios relatively quickly. Detailed modelling might take longer, but preliminary results should have been available. Why didn't NASA present those details? Several possibilities exist. Perhaps the analysis is still ongoing. Maybe the excitation modeling is more complex than usual, requiring additional work to convert intensities to reliable abundance estimates. Maybe peer review for publication is still in progress, and the team doesn't want to present detailed results publicly before they're formally published. These are legitimate scientific workflow considerations. Perhaps the results are ambiguous or uncertain. Maybe different analysis approaches give different answers for the abundance ratios. Maybe there's disagreement within the team about interpretation. Rather than present controversial or uncertain preliminary findings, NASA might have chosen to wait for better clarity. Again, this is reasonable. You don't want to announce results you're not confident about. Perhaps the results are unusual enough that they warrant additional verification before public discussion. If the nickel enrichment is dramatic and doesn't have obvious natural explanations, that's something you'd want to check very carefully before announcing. Not because of conspiracy, but because extraordinary claims require extraordinary evidence. You verify, re-verify, check for instrumental artifacts, run the analysis multiple ways, and make sure you're not being fooled by something. Systematic before you tell the world you found something strange. Or perhaps, and this is the explanation that frustrates the astronomy community, NASA simply chose not to dive into technical details during a public briefing aimed at general audiences. The presentation was carefully managed for broad accessibility. Getting into nickel to iron ratios, excitation modeling, and abundance derivation techniques might have seemed too technical for the format they'd chosen. If that's the explanation, it represents a misjudgment of audience interest. The people who followed 3IATLAS closely enough to watch a NASA press conference about it aren't looking for surface-level reassurance. They want detailed information. They want to see the data, understand the analysis, and draw their own conclusions. Withholding technical details to maintain accessibility paradoxically makes the presentation less satisfying to the core interested audience. The nickel question connects to broader composition issues that also didn't get adequate attention. 3IATLAS releases more carbon dioxide than water, according to JWST observations from August. That's unusual. Most solar system comets are water-dominated. The high CO2 ratio suggests formation in a particularly cold environment, or perhaps substantial processing during the billions of years the comet has spent in interstellar space. Galactic cosmic rays, high-energy particles streaming through interstellar space can chemically alter surface materials over time. They can break molecular bonds, create new chemical species, and generally weather exposed ices. A comet drifting through interstellar space for billions of years would experience substantial cosmic ray exposure, potentially altering its surface composition in ways that make it distinct from solar system comets that formed more recently and haven't experienced as much exposure. The James Webb observations should have revealed isotopic ratios as well. Different isotopes of hydrogen, carbon, oxygen, nitrogen. These ratios tell you about formation conditions and processing history. Deuterium to hydrogen ratio, in particular, is a powerful diagnostic of formation temperature. Did JWST measure these ratios? The instruments are certainly capable of it. If so, what did they show? We don't know because NASA didn't present that information. Similarly, MAVEN's ultraviolet observations should constrain the deuterium to hydrogen ratio in the hydrogen coma surrounding the comet. That data was mentioned during the briefing but not discussed in detail. What was the ratio? How does it compare to solar system comets? To interstellar clouds? To predictions for comets formed in other stellar systems? All of this compositional information exists somewhere. The instruments captured it. Researchers are presumably analysing it. But, as of the November 19th presentation, the public understanding of 3IATLAS's composition remains frustratingly incomplete. We know it has water, CO2, cyanide, and nickel. We know the CO2 seems enhanced relative to water. We know nickel is present in detectable amounts, with a ratio to iron that's apparently unusual. But we lack the quantitative details, the isotopic measurements, the spatial distribution information, the time evolution data, all the specifics that would let us actually understand what 3IATLAS's composition tells us about its origin and history. This is information that should have been presented in November, 3.5 months after JWST observations. more than 2 months after VLT spectroscopy. Plenty of time for preliminary analysis of data that, again, doesn't require years to process. The absence of this information in the official presentation contributes to the sense that NASA provided a surface-level update when the community wanted and deserved depth. The nickel detection got a brief mention, being investigated, and the presentation moved on. That's not adequate for what might be one of the most chemically interesting aspects of this interstellar visitor. Whether there are natural explanations for the compositional anomalies, and there almost certainly are, we can't evaluate them without the data. And without being able to evaluate competing explanations, we're left with unanswered questions and the uncomfortable feeling that more is known internally than was shared publicly. That feeling of incomplete disclosure, whether justified or not, colours how observers interpret everything else about NASA's handling of 3IATLAS. When you combine the blurred high-rise images, the jet structure that doesn't obviously make sense given rotation, the missing spectroscopic details, and the superficial treatment of composition, it creates a pattern of under-delivery that's difficult to ignore. And we haven't even gotten to the brightness surge yet, which presents its own set of puzzles that NASA glossed over during the briefing. Between early October and early November 2025, 3IATLAS brightened by approximately a factor of 5 in visible wavelengths. That's a 2-magnitude increase in astronomical terms, a substantial change that transformed the comet from a faint object requiring decent-sized telescopes to something approaching the threshold of visibility in smaller instruments. Comets brightening as they approach the Sun is entirely expected. This is basic comet physics. As distance from the Sun decreases, solar radiation intensity increases according to the inverse square law. More energy hits the comet's surface. Surface temperatures rise. Volatile ices that were stable farther out begin to sublimate. Activity increases. More gas and dust fill the coma. More material scatters sunlight back toward observers. The comet gets brighter. This process is so well understood that astronomers can predict comet brightness with reasonable accuracy based on distance from the Sun and empirical relationships derived from observing hundreds of other comets. The predictions aren't perfect. Individual comets vary based on composition, rotation, active region, distribution, and other factors, but the general trend is reliable. So when NASA mentioned that 3IATLAS brightened around perihelion, that fits expectations perfectly. Comets do this. Nothing unusual. Except, when you look at the specific numbers and timing, the straightforward story gets more complicated. Let's start with the magnitude of the change. 5-fold increase in brightness means 5 times as much light reached observers from the comet in early November compared to early October. For a comet already active and producing a substantial coma, achieving 5-fold brightening requires a significant increase in either the amount of material in the coma or the efficiency with which that material scatters light, or both. The standard explanation invokes increased surface activity. As perihelion heating penetrates deeper into the nucleus, buried ice layers reach sublimation temperatures. New active regions develop or existing ones intensify. The surface area undergoing sublimation increases. More gas releases. More dust lofts into the coma. Total brightness increases proportionally. Think of it like turning up the intensity on multiple garden sprinklers simultaneously. Each individual sprinkler might not change much, but if you activate several new ones and increase flow on existing ones, the total amount of water spraying into the air goes up substantially. Same principle with comets. More active area plus more intense activity per unit area equals significantly more material in the coma. For many comets, this explanation works perfectly. You see steady brightening as perihelion approaches, a peak near closest approach to the Sun, then gradual dimming as the comet recedes and activity decreases. The shape of the brightness curve matches thermal models that calculate how deep solar heating penetrates and how quickly different ice layers sublimate. But 3IATLAS's brightening has some features that complicate the simple thermal model. First, the timing. The 5-fold increase occurred between early October and early November. Perihelion was October 29th, so the brightening extended through perihelion and continued after. Post-perihelion brightening isn't impossible. Thermal inertia means the nucleus can continue warming even after beginning to recede from the Sun, but achieving maximum brightness weeks after perihelion is somewhat unusual. Most comets peak in brightness at or shortly after perihelion, then begin dimming as decreasing solar intensity reduces sublimation rates. Extended post-perihelion brightening can happen if the nucleus is rotating such that particularly active regions come into sunlight only after perihelion, or if there's a delay between when heat penetrates to subsurface ice layers and when those layers actually begin sublimating vigorously. Second, the magnitude. Five-fold brightening from an already active comet requires substantial new material. The coma isn't empty space, it's already filled with gas and dust from earlier activity. To make it 5 times brighter means adding enough new material to the coma to quintuple the total amount of light being scattered. How much material is that? It depends on dust particle sizes and reflectivity, but you can estimate roughly. If the coma was already containing, say, 10 billion kilograms of dust and gas, you'd need to add another 40 billion kilograms to achieve 5-fold increase. That's crude, but it gives you the scale. You're talking about sublimating and ejecting tens of billions of kilograms of material over a period of several weeks. Now let's connect this to the nucleus size. Current estimates place the nucleus diameter at perhaps 1 kilometer or less. For a spherical nucleus 1 kilometer in diameter, the surface area is approximately 3.1 million square meters. That's the total area available for sublimation. But not all of that surface is active. Comets typically have some fraction covered by inactive dust mantles that insulate subsurface ice. The active fraction might be 10%, maybe 20% on a particularly vigorous comet. Let's say 20% of 3IATLAS's surface area is actively sublimating, that's roughly 620,000 square meters. To eject 40 billion kilograms from 620,000 square meters over, say, 4 weeks, means each square meter needs to sublimate approximately 2,500 kilograms. That's 2.5 metric tons per square meter over a month, or roughly 83 kilograms per square meter per day. Is that plausible? Let's check the energetics. At 3IATLAS's perihelion distance of 1.36 AU, the solar constant is approximately 1,000 watts per square meter. Not all of that energy goes into sublimation. Some reflects, some heats the surface without causing sublimation, some radiates away as infrared. Let's generously assume 50% efficiency, giving 500 watts per square meter available for sublimation. The energy required to sublimate ice depends on which ice. For water ice, the latent heat is about 2.8 million joules per kilogram. For carbon dioxide ice, it's about 600,000 joules per kilogram. 3IATLAS apparently has more CO2 than water, so let's use 600,000 joules per kilogram as a representative value. To sublimate 83 kilograms per day from 1 square meter requires about 50 billion joules per day, or roughly 580,000 watts. But we only have 500 watts available per square meter from solar heating. We're short by a factor of over 1,000. Even if we assume 100% efficiency, every single joule of solar energy goes into sublimation. Nothing lost to reflection or radiation. We still only have 1,000 watts per square meter, still short by a factor of more than 500. The numbers don't add up. Either the nucleus is much larger than current estimates suggest, or the active fraction is much higher than typical, or the sublimation rate per unit area is lower than my calculation, or the brightness increase requires less mass than I estimated. All of these are possible. My calculation used rough estimates at every step. The actual numbers could differ, but the exercise illustrates that 5-fold brightening from a small sub-kilometer nucleus requires pushing the limits of what solar heating can accomplish. It's not obviously impossible, but it's energetically challenging. This connects to another possibility that didn't get discussed during NASA's presentation: partial fragmentation. If pieces of the nucleus broke away during perihelion, exposing fresh interior ice, that would dramatically increase active surface area without requiring the intact nucleus to suddenly become much more active per unit area. Fragmentation is common among comets during close solar approaches. Thermal stresses crack weakly bound materials. Differential heating creates mechanical tensions. Volatile pockets under dust layers can erupt violently, blowing off overlying material. Many comets show evidence of shedding pieces, ranging from tiny dust fragments to kilometer-sized chunks. The November 11th images by Jewett and Liu showed 3IATLAS as a single intact nucleus. But those observations have limited resolution. They could detect kilometer-scale fragmentation but would miss smaller pieces. If the nucleus shed meter to 100-meter-sized chunks, those wouldn't be visible, but could contribute substantially to brightness if they exposed fresh ice. Think of it like breaking apart an ice cube. The total mass doesn't change, but the surface area increases dramatically. More surface means more area for sublimation. If several large fragments, each with their own active surfaces, exist near the main nucleus, the combined brightness could easily increase by factors of 2 to 5 compared to the intact body. NASA addressed fragmentation explicitly. No evidence for breakup was found, but what they mean by breakup matters. Major catastrophic fragmentation into multiple comparable-sized pieces would have been obvious. Minor shedding of smaller fragments might not show up in available imagery yet could still affect brightness substantially. Third possibility, changing dust to gas ratio. Brightness depends not just on how much material exists in the coma, but also on that material's light scattering efficiency. Dust particles scatter sunlight far more effectively than gas molecules. A coma with high dust content appears much brighter than a gas-dominated coma with the same total mass. If perihelion activity changed the dust-to-gas ratio, perhaps by exposing dustier layers of the nucleus or by changing the vigor of gas outflows such that more dust gets lofted, brightness could increase disproportionately to mass increase. You'd get more brightness per kilogram of ejected material if the dust fraction rose. This is plausible. As ice sublimates, it leaves behind dust that was originally mixed with the ice. If dust accumulates on the surface, later outgassing has to punch through this dust layer, carrying dust particles along with the gas. The dust content in the coma reflects this complex interplay between how fast ice sublimates and how efficiently gas can entrain and lift dust. Fourth possibility, geometric effects. As viewing geometry changes, observers see different faces of the coma and different aspects of the dust distribution. If more active regions rotated into view facing Earth in November compared to October, we'd see brighter emissions simply because we're looking at a more active hemisphere. Similarly, if the dust tail became better aligned with our line of sight, the integrated brightness increases because we're seeing more of the tail's total light scattering material along a longer path through the coma. These geometric effects are real and can contribute to perceived brightness changes, but they typically don't produce five-fold increases by themselves. Geometry might account for 20 or 30% variation, perhaps doubling under favourable circumstances, but quintupling seems too large for purely geometric explanations. Most likely, the true explanation combines multiple factors: some fragmentation exposing new ice, some deepening of solar heating penetration, activating subsurface layers, some change in dust-to-gas ratio making the coma more efficient at scattering light, some favourable geometric evolution improving visibility, all contributing together to produce the observed five-fold increase. But here's what frustrates observers. NASA's presentation didn't explore any of this. The brightening was mentioned. It was framed as normal cometary behaviour. And that was it. No discussion of whether the energetics work for the estimated nucleus size, no analysis of what mass loss rates the brightness implies, no consideration of whether fragmentation might have played a role despite the November 11th imaging, no modelling of how dust-to-gas ratios might have evolved. These aren't peripheral details. They're central to understanding what 3IATLAS did during its most active phase. The brightening is directly observable data that constrains physical processes occurring on and near the nucleus. Explaining it quantitatively tells you about the nucleus composition, structure, activity level, and response to solar heating. That's the kind of analysis the astronomical community expected from NASA. Deep dives into the physics, models showing whether observed behaviour matches predictions, quantitative assessments of whether anomalies exist or whether everything fits comfortably within understood processes. Instead, the presentation treated complex phenomena with brief acknowledgements and reassurances. Yes, the comet brightened. Yes, comets do that. Moving on. This pattern acknowledging unusual features, then moving on without detailed analysis, repeated throughout the briefing. And it's one of the primary reasons observers felt the presentation fell short. We wanted depth, we got surface-level summary, and the frustration intensified when we considered that all the tools for providing depth were available. The observations existed, the instruments had collected the data, months had passed for analysis, yet the public presentation remained frustratingly shallow on precisely the aspects that made 3IATLAS scientifically compelling. The brightness surge connects to another question that barely received attention. What does the mass loss imply about the comet's longevity and structure? If 3IATLAS shed tens of billions of kilograms during perihelion passage, and if its total mass is estimated based on a sub-kilometer nucleus, you can calculate what fraction of its initial mass was lost. Avi Loeb did exactly this calculation and published it in a Medium post. Based on the non-gravitational acceleration measurements and the observed jet structures, he estimated that 3IATLAS lost more than 13% of its initial mass during perihelion. That's substantial. Most comets lose only a few percent per perihelion passage. 13% mass loss raises interesting questions. If accurate, it suggests either the comet is unusually volatile rich, packed with easily sublimated ices rather than bound tightly with refractory dust, or the perihelion passage was unusually violent for this comet, perhaps because it's the first time in billions of years that it experienced such intense solar heating. The latter possibility has appeal. If 3IATLAS formed around another star billions of years ago and has been drifting through cold interstellar space ever since, this October perihelion represents its first encounter with significant stellar radiation in eons. The surface would have been pristine, no protective dust mantle built up from previous perihelion passages, unlike solar system comets that have passed through the inner solar system multiple times. Fresh, unprocessed ice exposed directly to sunlight would sublimate vigorously. The first perihelion passage for an interstellar comet might be dramatically more active than subsequent passages would be if the comet were captured into a closed orbit. That could explain unusually high mass loss and brightness surge. This is virgin ice, seeing sunlight for the first time in billions of years. But again, NASA didn't discuss this. The mass loss estimates weren't presented. The implications for nucleus structure and composition weren't explored. The comparison between first passage interstellar comets and multi-passage solar system comets didn't appear in the briefing. These omissions matter because they leave major aspects of 3IATLAS's behavior unexplained in the public record. Amateur observers documenting the comet's evolution don't have access to the detailed models and data analysis that NASA does. They depend on official presentations to provide context and interpretation for what they're seeing. When that context and interpretation remain absent or superficial, it creates a vacuum that speculation fills. Not necessarily bad speculation, often thoughtful, physics-based attempts to understand what's happening, but speculation nonetheless, because the authoritative analysis that should ground the discussion hasn't been publicly provided. The fifth major unexplained area compounds this frustration: the trajectory and timing anomalies that, when considered together rather than individually, create a statistically improbable situation that deserves more careful examination than NASA gave it. Let's talk about probability and what it means when multiple, low-probability events occur simultaneously. 3IATLAS approaches our solar system on a trajectory that lies within approximately 5 degrees of the ecliptic plane. The ecliptic is the flat disk where Earth and the major planets orbit. It's a thin slice through three-dimensional space. If you imagine the solar system as a coin, the ecliptic is like the coin's face, with a little bit of thickness, but mostly just a flat surface. Objects approaching from random directions in interstellar space should arrive at any angle relative to this plane. Think about it. The galaxy is three-dimensional. There's no preferred direction. An object ejected from another star system thousands or millions of years ago has no reason to arrive aligned with our particular planetary disk. It could come from above, below, or any angle in between. Mathematically, if you want to calculate the probability that a random arrival direction falls within 5 degrees of the ecliptic, you're asking what fraction of a sphere's surface area lies within that thin band. The answer is approximately 0.2%. Out of 1,000 random interstellar objects, you'd expect about 2 to arrive within 5 degrees of the ecliptic. Now, we've only confirmed 3 interstellar objects total. 3 is not a large enough sample to draw statistical conclusions. With 3 observations, you can't say whether the 0.2% probability matters. Random chance alone could easily produce 1 ecliptic-aligned object out of 3. But here's where things get interesting. It's not just the ecliptic alignment, it's the combination of factors. 3IATLAS's trajectory brought it within approximately 29 million kilometers of Mars on October 3rd. That's close enough for Mars orbiters to photograph the comet with decent resolution. Pure coincidence? Perhaps, but Mars represents a tiny target in the vastness of space. An object on a random interstellar trajectory has no particular reason to pass near Mars. The trajectory also brought 3IATLAS within approximately 97 million kilometers of Venus on November 3rd, and will bring it within approximately 54 million kilometers of Jupiter on March 16th, 2026. Again, individual encounters aren't impossible. There are several planets, and space is large but not infinite. But passing near multiple major planets during a single solar system, traverse starts pushing the boundaries of what random trajectory typically produces. Then there's the timing. 3IATLAS reached perihelion on October 29th, when Earth was on the opposite side of the Sunday. For 10 days surrounding perihelion, the period when comets typically show their most intense activity, ground-based observations from Earth were impossible. The comet was lost in solar glare, hidden behind our star from our perspective. This isn't common, but isn't rare either. Given the comet's orbit and Earth's position, there was perhaps a 5% chance that perihelion would occur when Earth was on the wrong side of the Sun for observation. Not incredibly unlikely, but not the expected case either. Now let's think about these factors in combination. The probability that an interstellar object arrives within 5 degrees of the ecliptic is 0.2%. The probability that it passes within 30 million kilometers of Mars is difficult to calculate precisely without knowing the exact trajectory details, but it's certainly less than 1%. Mars is a small target. The probability that perihelion occurs when Earth is on the far side of the Sun is around 5%. If these were independent factors, if one didn't influence the others, you'd multiply the probabilities to get the combined probability. 0.2% times 1% times 5% gives you 1 in 100 million. That would be extraordinarily unlikely. But these factors aren't independent. The ecliptic alignment actually makes planetary encounters more likely because the planets orbit in the ecliptic. If your trajectory lies in the ecliptic plane, you're much more likely to pass near planets than if you approach from a steep angle. So the combined probability isn't 1 in 100 million, it's higher, maybe 1 in several thousand or tens of thousands. Still, when you consider that we've observed only 3 interstellar objects ever, finding one with this particular combination of characteristics is noteworthy. Not impossible, not proof of anything unusual, but noteworthy enough that it deserves more attention than NASA gave it. During the November 19th presentation, the ecliptic alignment received brief mention. The trajectory was shown on graphics. The Mars encounter was highlighted as providing good observational opportunities, but the statistical improbability of this particular configuration wasn't discussed. The coincidental timing that hid perihelion from Earth wasn't examined as potentially interesting rather than just unfortunate. This matters because patterns in data sometimes reveal underlying processes we didn't anticipate. When seemingly unrelated characteristics cluster together in ways that are individually plausible but collectively unusual, that's often a hint that something interesting is happening. Let me give you a terrestrial analogy. Imagine you're studying wild animals in a forest. You observe that a particular animal is active only at night. Okay, lots of animals are nocturnal. Not unusual. You notice it prefers hunting near water sources. Again, many animals do this. Not surprising. You observe it has excellent hearing, common among predators, nothing strange. Each characteristic individually is unremarkable. But if you found an animal that was nocturnal and hunted near water and had exceptional hearing and avoided moonlit nights and preferred areas with dense vegetation, you'd start to think these characteristics might be connected. Maybe this animal is specifically adapted for hunting fish in dark, overgrown streams. The pattern tells you something about evolutionary pressures and ecological niche that you wouldn't see by looking at each trait separately. 3IATLAS's characteristics might be similar. Ecliptic alignment could be random. Multiple planetary encounters could be coincidental. Perihelion timing could be bad luck. But when you see all these factors together in a single object, the only ecliptic-aligned interstellar visitor we've detected, arriving at a time when it passes near 3 major planets while hiding its most active phase from Earth's view, it starts to feel like more than just accumulated coincidences. Now, I want to be clear about what I'm not saying. I'm not suggesting 3IATLAS was deliberately targeted at our solar system. I'm not claiming the trajectory indicates artificial origin. The physics doesn't support that. Without propulsion systems capable of course corrections, and we have no evidence for such systems, an object can't target anything. It simply follows the trajectory that gravitational interactions over millions of years have given it. What I am saying is that the combination of characteristics creates a statistically interesting situation that warrants more thorough examination than it received. NASA should have discussed the cumulative probability explicitly. They should have addressed why this particular configuration occurred and whether it tells us anything about the population of interstellar objects or observational biases in how we detect them. One possibility is selection bias. Maybe interstellar objects near the ecliptic are easier to discover because that's where survey telescopes focus their searches. Most near-Earth object surveys concentrate on the ecliptic because that's where asteroids and comets that might threaten Earth reside. If your telescope spends 90% of its time looking at the ecliptic region and only 10% looking at higher inclinations, you'll naturally find more ecliptic-aligned objects. If this explains 3IATLAS's alignment, it means the true population of interstellar objects might be more randomly distributed, but our detection methods bias us toward finding those near the ecliptic. That's scientifically important. It means we need to correct for observational bias when we try to estimate how many interstellar objects pass through the solar system. But the previous interstellar objects don't support this explanation strongly. Oumuamua arrived at about 44 degrees inclination to the ecliptic, not aligned. 2I Borisov came in at about 41 degrees, also not aligned. If survey bias strongly favoured ecliptic objects, we should have found more ecliptic-aligned visitors. Instead, 2 out of 3 weren't aligned, and the one that is aligned is the current object generating questions. Another possibility is that ecliptic-aligned interstellar objects are genuinely more common for physical reasons. Perhaps the Milky Way's galactic disk has some structure or velocity distribution that makes objects escaping from other star systems more likely to travel in certain directions. Perhaps the sun's motion through the galaxy creates a preferential encounter geometry. This seems unlikely. The galaxy is pretty isotropic on the scales relevant to interstellar object trajectories, but it's not impossible. If a physical reason exists for ecliptic alignment to be more common, that would be fascinating. It would tell us something about galactic dynamics and how interstellar material moves through the galaxy. A third possibility is simply that with a sample size of 3, we're seeing statistical noise. 3 objects isn't enough to establish patterns. Maybe the next 10 interstellar objects we detect will all come from high inclinations, and 3IATLAS will look like the outlier. Sample size matters enormously in statistics, and our current sample is absurdly small. But even acknowledging small sample size, the specific combination of factors in 3IATLAS ecliptic alignment plus multiple planetary encounters plus perihelion timing is unusual enough that dismissing it as pure chance without examining it carefully seems like missed opportunity. NASA's presentation treated each factor individually and found each unremarkable ecliptic alignment interesting, but within possibilities. Mars encounter provided good observation opportunities. Perihelion timing, unfortunate for Earth-based observers. Each treated in isolation, none flagged as particularly significant. But that's not how probability works with correlated events. You have to consider the pattern, not just the individual components. Avi Loeb makes exactly this point in his Medium articles. He lists 12 anomalies of 3IATLAS. Looking at any one individually, you can find natural explanations. But looking at all 12, together, the trajectory, the timing, the composition, the jets, the brightening, the rotation puzzle, The anti-tail persistence, the cumulative picture, is of an object that sits at the edge of normal comet behavior across multiple independent characteristics. Loeb proposes a Loeb scale ranking system, where 0 represents definitely natural and 10 represents definitely technological. He initially placed 3IATLAS at around 4 more unusual than typical comets, but not so anomalous that natural explanations are ruled out. That's a defensible position. It acknowledges that something interesting is happening without jumping to extraordinary conclusions. The scientific approach is to take that acknowledgement seriously, to say, yes, we see this pattern of unusual characteristics. Let's investigate carefully to understand whether natural explanations truly account for everything, or whether we're missing something about how interstellar objects behave. That investigation requires detailed analysis, modeling whether the jet structures can result from plausible nucleus configurations and rotation states, calculating whether the brightness evolution matches expected thermal response for reasonable nucleus properties, examining whether the composition ratios are consistent with known formation processes or require unusual conditions. NASA has the resources to do this analysis. They have the experts, the computational tools, the data, and the institutional knowledge. This is exactly the kind of deep scientific investigation that justifies NASA's budget and mission. But in the November 19th presentation, that depth was absent. The anomalies were individually noted, then explained away with brief reassurances. The cumulative pattern wasn't addressed. The statistical improbability of the combination wasn't discussed, and this creates the impression, fairly or not, that NASA is more interested in emphasizing normalcy than exploring mystery, more concerned with public reassurance than scientific investigation, more focused on controlling the narrative than engaging with genuine puzzles. I want to emphasize, I don't think NASA is hiding information or covering up anything extraordinary about 3IATLAS. The far more likely explanation is that institutional incentives push toward caution and reassurance when dealing with high-profile public interest topics. Better to understate uncertainty than to generate speculation. Better to present confident conclusions than to acknowledge how much we don't yet understand. That's a reasonable institutional strategy for maintaining public trust and avoiding misinformation. But it comes at a cost. The cost is that observers who look carefully at the data, professional astronomers, informed amateurs, people who understand the physics, recognize when the official narrative is overly simplified. They see the gaps between what's presented and what the data actually shows. And that recognition breeds skepticism about whether they're getting the complete story. Which brings us to perhaps the most significant gap in NASA's presentation, the institutional and philosophical issues that the 47-day delay and the ultimate content of the release revealed. The 3IATLAS situation illuminates tensions that extend far beyond this specific comet. These tensions involve how science operates in the 21st century, how institutions balance competing priorities, and what the public should expect from agencies funded by taxpayer dollars to explore space on humanity's behalf. Let's start with transparency. Science fundamentally depends on open sharing of data and methods. The scientific process works because results are published, data are made available, other researchers can verify findings, and knowledge builds cumulatively. This openness is not optional, it's essential to how science distinguishes itself from other ways of knowing. When NASA captures images or data, especially on missions funded by public money, there's a strong argument that this information belongs to humanity. It should be shared as widely and quickly as possible, not just the processed results, but the raw data that allows independent analysis. This philosophy has driven major successes. The Hubble Space Telescope's data archive, for example, has enabled countless discoveries by researchers who weren't original observers. Making data public maximizes its scientific value. But complete immediate transparency faces practical challenges. Raw data from sophisticated instruments isn't immediately usable. It requires calibration, artifact removal, and processing before it provides reliable information. Releasing uncalibrated data could mislead researchers who don't understand the instrumental effects. So some processing delay is legitimate. Additionally, there's the question of proprietary periods. Researchers who propose observations and invest effort into T. Planning them reasonably expects some time to analyze the data before others use it. This incentivizes the proposal process and rewards the scientists doing the work. Typical proprietary periods range from 6 months to a year, after which data becomes fully public. For 3IATLAS, the situation differs because this wasn't a planned observation campaign with specific scientific proposals. The comet appeared, and various missions opportunistically turned instruments toward it as schedules allowed. No one owns the data in the traditional sense. It's more like data of opportunity that arguably should flow quickly to the community. Yet the release took 47 days from image capture to public presentation. Even accounting for the government shutdown, which consumed about 5 weeks of that time, the timeline raised questions. Compare this to how amateur astronomers operate. When Ray's astrophotography captures images of 3IATLAS, those images appear online within hours. There's no institutional review, no multi-level approval, no coordination with communication departments. Just an observer sharing what they found. Professional astronomy used to work similarly. Telegram systems and rapid publication mechanisms allowed discoveries to reach the community within days. As instrumentation became more complex and institutional structures grew more elaborate, the pace of sharing slowed. What used to take days now takes weeks or months. Is this progress or regression? It depends on perspective. From NASA's viewpoint, the delay allowed careful verification of results. The high-rise images, despite not being perfect, were at least properly calibrated and understood before release. The presentation was comprehensive, including observations from multiple missions rather than piecemeal releases. The messaging was coordinated to avoid confusion. These are legitimate institutional priorities. From the community's viewpoint, the delay impeded scientific progress. Researchers couldn't incorporate high-rise data into their ongoing analysis. Observation strategies couldn't be optimized based on the best available information. Amateur networks filled the gap, but they shouldn't have had to. NASA's instruments are superior and their data should have been available. This tension between institutional caution and scientific urgency plays out constantly in modern science. Large institutions tend toward conservatism. Multiple stakeholders need to approve releases: scientists, administrators, legal reviewers, public affairs officers. Each adds delay. Each has legitimate concerns. But cumulatively, the process becomes slow enough that it interferes with the science itself. The question becomes, what should NASA prioritize? If forced to choose between cautious, well-packaged presentations that take months to prepare versus rapid, rough releases that get information out quickly, which serves science better? There's no universal answer. Different situations merit different approaches. For planetary defense, tracking asteroids that might threaten Earth, rapid release is essential. Lives could depend on quick information flow. For deep space astrophysics, studying events millions of light years away, taking time for careful analysis probably makes sense. 3IATLAS falls somewhere between. It's not threatening anyone, but it's rare, only the third interstellar object ever confirmed. It's time sensitive, the object is moving through the solar system, and optimal observation windows pass quickly. It's scientifically valuable, each data point helps constrain models of interstellar objects, and it's high interest, the public is genuinely curious and engaged. For this kind of target, the argument for rapid release seems strong. Not instant, allow a week or two for basic calibration and quality checks, but weeks, not months. Certainly not 47 days for images that ultimately weren't technically better than what amateurs achieved. The China comparison makes this tension stark. Tianwen-1 released images within days. Were those images perfectly calibrated? Probably not. Were they scientifically useful despite that? Absolutely. The astronomy community appreciated having them. They informed ongoing observations and analysis. They demonstrated scientific openness. NASA's more cautious approach, even if we accept the shutdown as explanation for most of the delay, created frustration precisely because the careful process didn't produce obviously superior results. If you're going to take 47 days, the payoff should be images and analysis that justify the wait. When amateur observers produce better documentation using equipment 1,000 times cheaper, It raises uncomfortable questions about whether the institutional caution actually serves its intended purpose. This connects to broader questions about scientific communication. How should space agencies present results when uncertainty exists? The traditional scientific approach is to present data, acknowledge uncertainties, show error bars, discuss alternative interpretations, and let the evidence guide conclusions. Scientific papers are full of phrases like consistent with, suggests, cannot rule out, and requires further investigation. This hedged language reflects honest uncertainty and invites further work, but public communication often simplifies this complexity. Uncertainty gets minimized. Confidence gets projected even when privately scientists have doubts. This happens for several reasons. First, simplification aids understanding. General audiences don't want detailed statistical analysis, they want to know what was found. Boiling down complexity into clear statements helps people grasp the significance. Second, confidence prevents misinformation. If NASA presented 3IATLAS with heavy emphasis on uncertainties and mysteries, media coverage might sensationalize the unknown aspects. NASA baffled by mysterious interstellar object makes for better headlines than NASA studies interstellar comet. Findings mostly match expectations. To prevent sensationalism, agencies present confident conclusions, even when internal discussions are more nuanced. Third, institutional credibility depends on appearing competent. Admitting we don't fully understand this could undermine public confidence in NASA's capabilities. Better to project expertise and control, even if the reality involves substantial uncertainty. These motivations are understandable, but they create a gap between public presentation and scientific reality. Observers who understand the science can see through the simplified messaging. They recognize when uncertainties are being glossed over, and that recognition can breed cynicism about whether official communications are trustworthy. The 3IATLAS presentation embodied this tension. The official message was clear: natural comet, behaving as expected, nothing unusual, science proceeding normally. But observers looking at amateur images showing complex jet structures, reading about nickel composition anomalies, and calculating rotation versus jet collimation probabilities knew the reality was more complicated. That mismatch between simplified official messaging and complex underlying reality frustrates scientifically literate observers. They don't need hand-holding or reassurance. They want honest grappling with puzzles. They appreciate when agencies say, "This is weird and we're working to understand it," more than when agencies say everything is normal, while clearly some things aren't quite normal. There's also a philosophical dimension to this. Science at its best embraces uncertainty. The frontiers of knowledge are where we don't yet have answers. Mystery is what makes science exciting. Admitting what we don't understand invites participation and engagement. Contrast two approaches to communicating about 3IATLAS. Approach A. 3I. Atlas is a natural comet. Our observations confirm it behaves as expected. Spectroscopy shows typical cometary composition. Jets result from sublimation. Brightness increased due to solar heating. Everything fits standard models. Approach B. 3IATLAS displays several characteristics we don't fully understand yet. The jet structures appear more tightly collimated than we'd expect, given the rotation rate we're working to determine whether intermittent emission or other factors explain this. The nickel-to-iron ratio seems unusual, and we're analysing whether this reflects formation conditions or measurement complexities. The brightness surge was dramatic, and we're modelling whether the energetics work for the nucleus size. These puzzles make this interstellar visitor particularly interesting, and we're excited to gather more data in December to help solve them. Which approach better serves science? Which builds more public engagement? Which honestly reflects the state of knowledge? I'd argue approach B is superior on all counts. It's more honest. It's more engaging. It invites people into the scientific process rather than presenting science as a finished product handed down by authorities. It treats the audience as capable of handling uncertainty rather than needing reassurance. But institutions gravitate toward approach A. It's safer, it's cleaner, it's less likely to generate uncomfortable questions or headlines. And therein lies the tension. NASA's November 19th presentation was firmly in the Approach A category. Confident conclusions, minimal acknowledgement of puzzles, emphasis on normalcy. For many observers, especially those who followed 3IATLAS closely, this felt like a missed opportunity. The opportunity wasn't just scientific though. Detailed analysis of the anomalies would have advanced understanding. It was also cultural. This was a chance for NASA to demonstrate that science is exciting precisely because it involves mysteries, that not everything fits neatly into boxes, that interstellar visitors can surprise us and challenge our models. Instead, the message was, nothing to see here, move along, it's just a comet. That message might prevent sensationalism, but it also prevents inspiration. It treats the public as needing protection from complexity rather than as potential participants in the excitement of discovery. There are many scientists at NASA and in the broader astronomy community who understand this and want more open, engaged communication. But institutional incentives and structures make that difficult. The pressure to maintain credibility, avoid controversy, and project competence pushes toward overcautious messaging. The result is situations like 3IATLAS, where the official presentation feels disconnected from the scientific reality, where observers with expertise recognize the gaps and oversimplifications, and where trust erodes because the messaging doesn't match what. Careful attention to the data reveals. How do we resolve this tension? There's no easy answer, but several principles might help. First, default to transparency. When in doubt, share more rather than less. Release raw data, even if analysis is ongoing. Trust the community to handle complexity. Second, embrace uncertainty publicly. Acknowledge puzzles explicitly. Describe what you don't understand. Invite collaboration and ideas. Third, separate technical communication from public outreach. Provide detailed technical presentations for specialists while also creating accessible summaries for general audiences. Don't try to serve both with a single middle ground approach that satisfies neither. Fourth, accelerate release timelines. Institutional review is necessary but can be streamlined. Aim for days or weeks, not months. Fifth, learn from the amateur community. Skilled amateurs demonstrate that rapid, open sharing doesn't compromise quality. Their collaborative, transparent approach often produces better science than secretive institutional processes. NASA has made enormous strides in openness over recent decades. The vast archives of Hubble, Spitzer, and other missions. The immediate public release of Mars rover images. The live streaming of major events. These represent genuine commitment to transparency. But there's room for improvement, and 3IATLAS highlights where institutional caution still impedes scientific progress. The 47-day delay, the superficial treatment of anomalies, the emphasis on reassurance over engagement with mysteries. These are areas where NASA could do better. And doing better matters not just for this one comet, but for all of science communication. Because when institutions lose the trust of informed observers, when their messaging diverges too far from the complex reality that careful analysis reveals, it becomes harder for those institutions to maintain credibility and support. The astronomical community isn't asking NASA to speculate wildly or embrace fringe theories. They're asking for honest, detailed, technically rigorous engagement with the data, for acknowledgement when things don't fit models perfectly, for transparency about uncertainties and ongoing investigations. That's not too much to ask from the world's premier space agency. And 3IATLAS provided a perfect opportunity to demonstrate that kind of openness. The opportunity was partially missed. Hopefully, future communications will learn from this experience. Which brings us to what happens next, and what we should be watching for as 3IATLAS approaches its closest point to Earth in less than a month, December 19th, 2025. Mark your calendar. That's when 3IATLAS reaches its closest approach to Earth at approximately 170 million miles, about 1.8 astronomical units. While that's still an enormous distance, more than twice as far as Mars orbits from the Sun, it represents the optimal observation window for ground-based telescopes and Earth-orbiting observatories. The geometry will be as favourable as it gets. The comet will be observable in the pre-dawn sky, climbing higher as winter progresses. For several weeks surrounding December 19th, we'll have the best opportunity to study this interstellar visitor in detail. What specifically should we be watching for? What observations would answer the open questions that NASA's presentation left unresolved? Let's walk through the key measurements and what they would tell us. First and most crucial, spectroscopic measurement of jet velocities. This is the test that distinguishes between natural sublimation and more exotic explanations. When gas molecules or atoms move toward or away from us, their spectral lines shift due to the Doppler effect, the same phenomenon that makes ambulance sirens change pitch as they pass. By measuring how much spectral lines are shifted, astronomers can determine how fast material is moving. For thermal sublimation at 3I, Atlas's distance from the Sun, velocities should be around 400 meters per second, maybe ranging from 200 to 600 meters per second, depending on which molecules you're observing and their specific thermal conditions. If December spectroscopy shows jets moving at these thermal velocities, it strongly supports natural sublimation. The material is moving at speeds consistent with solar heating, driving the outflow. No other energy source is needed. If spectroscopy shows jets moving at several kilometers per second significantly faster than thermal velocities, that would be genuinely puzzling. Where's the extra energy coming from? Subsurface pressure buildup could potentially explain it, but you'd need detailed modeling to show whether plausible scenarios actually produce the observed velocities. Both the James Webb Space Telescope and large ground-based instruments like Keck, the Very Large, Telescope, and Gemini can perform this spectroscopy. JWST in particular has the sensitivity and spectral resolution to measure velocity distributions accurately. If they turn these instruments toward 3IATLAS in December, which they almost certainly will given the scientific interest, we should get definitive velocity measurements within weeks. Those measurements will either confirm thermal sublimation or reveal something requiring deeper explanation. Either way, it's a clear, quantitative test that cuts through speculation. Second, updated rotation period measurements. We know 3IATLAS rotated every 16.16 hours in July and August. Has that changed? Monitoring brightness variations over multiple nights in December will reveal the current rotation period. If rotation has changed significantly, sped up, or slowed down substantially, that tells us the perihelion passage exerted strong torque on the nucleus. The asymmetric mass loss was powerful enough to alter angular momentum noticeably. That would help explain the straight jet collimation. If rotation slowed dramatically, the smearing effect would be reduced. If rotation is unchanged, we need to look elsewhere for explanations of the jet morphology. Intermittent emission becomes more likely. Or perhaps the jet structures we're seeing aren't continuous streams but discrete ejection events that don't reveal rotation the way continuous outflow would. The rotation measurement is straightforward. Any astronomer with decent equipment can contribute photometric data. Amateur networks will undoubtedly monitor this. The question is whether results will be compiled and analyzed quickly enough to inform public understanding during the observation window. Third, high-resolution imaging to look for fragmentation evidence. While November 11th images showed an intact nucleus, higher-resolution observations, or better seeing conditions, might reveal small fragments that weren't previously visible. If fragments exist, pieces ranging from tens of meters to hundreds of meters that separated during perihelion, they would help explain the brightness, surge, and potentially some of the jet structures. Multiple active surfaces would increase total sublimation area without requiring each piece to be extraordinarily active. The Hubble Space Telescope could potentially resolve large fragments if they exist and are sufficiently separated from the main nucleus. Ground-based adaptive optics systems on large telescopes might also achieve adequate resolution under excellent seeing conditions. Fourth, detailed composition analysis, including isotopic ratios. The James Webb Space Telescope should be able to measure deuterium to hydrogen ratios, carbon-13 to carbon-12 ratios, oxygen-18 to oxygen-16 ratios, and nitrogen-15 to nitrogen-14 ratios. These isotopic ratios encode information about formation temperature and subsequent processing. Deuterium abundance, for example, is highly sensitive to temperature cold formation environments to preserve more deuterium. The D to H ratio in 3IATLAS should tell us whether it formed in conditions similar to our solar system's Kuiper belt or in a much colder or warmer environment around its parent star. Comparing isotopic ratios between 3IATLAS and solar system comets will reveal whether interstellar comets show systematic differences, reflecting their formation around different stars with different chemical enrichment. Histories. Fifth, monitoring nickel emission over time. Is the nickel signature consistent across multiple observations, or does it vary as different regions of the nucleus become active? If nickel is heterogeneously distributed, watching it change over rotation periods would map where the nickel-rich material is located. Additionally, getting precise nickel-to-iron ratios from well-calibrated spectroscopy would finally nail down whether the ratio is genuinely inverted, more nickel than iron, or just unusually high for natural materials. With exact numbers, we could compare to meteoritic samples and models of material processing in different stellar environments. Sixth, mass loss rate measurements. By monitoring how brightness and coma size evolve, astronomers can estimate how much material 3IATLAS is currently losing. Combined with the estimated nucleus size, this tells us what fraction of total mass is being shed per unit time. If the mass loss rate is declining significantly compared to perihelion, as expected for a comet moving away from the Sun that supports normal thermal behavior, if mass loss remains high despite increasing distance from the Sun, that would be puzzling and might indicate subsurface heat sources or delayed response from deeply buried ice now becoming active. Seventh, jet morphology evolution. Will the complex multi-jet structure persist, or will it simplify as activity decreases with distance? If jets maintain their tight collimation over coming weeks and months, that strengthens the puzzle of how rotation doesn't smear them. If they start showing more typical spiral or curved structures, it suggests the straight appearance was a transient phenomenon related to perihelion conditions. High-quality amateur observations will continue to be valuable here. The networks that documented November's complex jet structures will keep monitoring through December and beyond. Their time series observations showing how structure changes will be scientifically valuable regardless of what professional instruments find. Eighth, non-gravitational acceleration refinement. As more position measurements accumulate with 3IATLAS now well separated from the Sun and easy to observe, the orbital solutions will improve. Better constraints on non-gravitational acceleration tell us about asymmetric outgassing quantitatively. If the measured acceleration remains at the current level of about 3.7 standard deviations, that's a solid detection of outgassing effects. If it increases with better data, it suggests more vigorous asymmetric activity than initially thought. If it decreases towards statistical insignificance, it might indicate the effect was transient during perihelion rather than ongoing. Ninth, coordinated multi-wavelength campaigns. Observing 3IATLAS simultaneously in optical, infrared, ultraviolet, and radio wavelengths reveals different aspects of the coma. Optical shows reflected sunlight from dust. Infrared shows thermal emission revealing dust, temperature, and size distribution. Ultraviolet reveals highly excited atomic and molecular species. Radio can detect molecules like hydrogen cyanide, methanol, and others that are difficult to observe at other wavelengths. A coordinated campaign with multiple observatories observing simultaneously produces a comprehensive picture of what's happening in the coma at a given moment. Different wavelengths probe different physical processes, and seeing them all together helps distinguish between competing models. NASA missions that observed 3IATLAS earlier, Hubble, JWST, MAVEN, and others, will likely turn back toward the comet in December. Their combined observations, if shared promptly this time, could provide the definitive characterization that November's presentation lacked. 10th, searching for new jets or structural changes. As different faces of the nucleus rotate into sunlight during December, new active regions might become visible. If the nucleus is highly heterogeneous, with some regions rich in volatiles and others depleted, we'd see jets turn on and off as rotation brings different areas into view. Monitoring for new features provides insights into nucleus structure and composition distribution. A uniform nucleus should show relatively steady activity. A patchy nucleus with localized ice deposits should show more variable behavior tied to rotation. 11th, polarimetry measurements. Observing how light from the coma is polarized tells you about dust particle properties, their size, shape, composition, and how they're distributed. 3IATLAS showed unusually high negative polarization in July and August observations, similar to trans-Neptunian objects. Continuing polarimetry as the comet evolves would reveal whether this property persists or changes as activity varies. Polarization provides a different way to study dust properties that complements direct imaging and spectroscopy. 12th, searching for sodium emission. Many comets show strong sodium emission from their coma, a bright yellow-orange glow visible in spectra. Sodium abundance varies widely between comets, and the reasons aren't fully understood. Some comets are sodium-rich, others sodium-poor. 3IATLAS's sodium emission hasn't been prominently reported yet. Observations specifically looking for this emission would add another compositional constraint. High sodium would suggest certain formation scenarios. Low sodium would suggest others. The December observation window represents a collective opportunity for the global astronomy community. Professional observatories, space telescopes, and amateur networks will all contribute. The key question is whether this data will be analysed and shared efficiently. If institutions repeat the November pattern, collecting excellent data but taking months to analyse and release it, the opportunity will be partially wasted. By the time results are published, 3IATLAS will have moved significantly farther away, and follow-up observations will be harder. The better approach would be rapid preliminary releases. Post-calibrated spectra publicly within days. Share images as they're processed. Put raw data in accessible archives immediately. Let the community work collectively rather than in isolated institutional silos. This is where amateur astronomy's culture of immediate sharing provides a model. When Ray's astrophotography or Gianluca Marsi capture new images in December, they'll appear online within hours. Professional institutions should strive for similar timescales, maybe not hours, but days rather than weeks or months. The scientific questions are clear. The observations needed to answer them are achievable with existing instruments. What remains uncertain is whether institutional processes will enable the rapid, collaborative, transparent science that this opportunity deserves. And here's something else to watch. How will NASA communicate December findings? Will they repeat the November approach, waiting for comprehensive analysis before saying anything, then presenting carefully managed conclusions, emphasizing normalcy? Or will they adopt a more dynamic approach, sharing preliminary results as they arrive, acknowledging uncertainties, and engaging the community in real-time interpretation? The latter would build far more goodwill and trust. It would demonstrate that lessons were learned from the November criticism. It would show institutional flexibility and responsiveness to community feedback. But institutional cultures change slowly. Old habits persist. The forces that led to 47-day delays and overly cautious messaging don't disappear overnight. So while we can hope for better communication approaches in December, we should prepare for the possibility that old patterns repeat. What's certain is that the astronomical community, professional and amateur alike, will be watching closely. Not just the comet, but also how institutions handle the data, the communication, the transparency. 3IATLAS has become a case study in scientific communication as much as a scientific target itself. The observations will happen, the data will be collected. The question is whether those data will be shared in ways that maximize their scientific value and build public engagement, or whether institutional caution will once again impede the open, collaborative science that works best. We'll know soon enough. December 19th approaches. The telescopes are ready. The community is eager. And 3IATLAS continues its journey through our solar system, carrying information from another star that we have just one chance to extract before it departs forever. We've travelled far in this investigation, from NASA's official presentation to the amateur observations that surpassed it, from the blurred high-rise images to the physics puzzles they failed to clarify, from composition mysteries to brightness anomalies, from institutional delays to questions about scientific transparency. Let's take a moment to synthesize what we've learned and what it means. First, the confirmed facts. 3IATLAS is definitively an interstellar comet. It came from beyond our solar system, shows active sublimation, has composition broadly consistent with icy bodies, and will leave our solar system never to return. These basics are not in dispute. NASA got that right. The object is natural. There's no evidence for artificial origin, no radio transmissions, no inexplicable accelerations that demand exotic explanations. Second, the genuine puzzles. The jet collimation across millions of kilometers, despite 16-hour rotation, isn't easily explained by standard models. Maybe intermittent emission solves it. Maybe rotation changed. Maybe we're misinterpreting what we see. But the puzzle is real. It deserves more attention than NASA gave it. The nickel composition anomaly, apparently more nickel than iron, ratios unlike solar system comets, sits uncomfortably with normal expectations. Maybe special formation conditions explain it. Maybe excitation effects create misleading emission ratios. Maybe heterogeneous nucleus structure is responsible. But without detailed public data, we can't evaluate competing explanations properly. The brightness surge requires energetics that push against what solar heating should accomplish for a sub-kilometer nucleus. Maybe partial fragmentation exposes more surface. Maybe the nucleus is larger than estimated. Maybe dust-to-gas ratios changed favorably. But the numbers are tight. It's at the edge of what seems plausible without additional assumptions. The trajectory alignment and timing collectively create a low probability situation. Maybe observation bias explains it. Maybe statistical noise with small sample size. Maybe nothing meaningful. But dismissing it without careful analysis seems premature given how unusual the configuration is. Third, the disappointment about institutional performance. NASA had advantages that amateur observers can only dream of. $720 million orbiters at Mars, the James Webb Space Telescope, resources, expertise, and access to data that no individual could match. Yet somehow, backyard astronomers produced better documentation of 3IATLAS's post-perihelion behavior than NASA's official release provided. That's not just disappointing, it's revealing. It suggests problems with how large institutions process and share information. The 47-day delay. The blurred images explained with technical limitations that may or may not fully account for the quality issues. The missing spectroscopic details 3 months after JWST observations. The superficial treatment of composition anomalies. The glossing over of physics puzzles. Each individually might have innocent explanations. Collectively, they create a pattern that erodes confidence in whether NASA is operating as effectively as its budget and mission demand. Fourth, the broader implications for science communication, the tension between transparency and caution, between engaging the public with mystery and reassuring them with confident conclusions, between sharing data rapidly to advance science and waiting for careful analysis to ensure accuracy. These tensions don't have perfect resolutions. But 3IATLAS demonstrated that erring too far toward caution creates its own problems. When official messaging diverges from what informed observers can see in the data, trust erodes. When amateur networks consistently outpace institutional releases, questions arise about whether institutional processes serve science or impede it. The astronomical community isn't asking for reckless speculation or premature conclusions. They're asking for honesty about uncertainty, depth of technical analysis, transparency about data, and speed of sharing that respects the time-sensitive nature of observing rare visitors. NASA can do better. Other space agencies, China's rapid Tianwen-1 release, ESA's regular updates demonstrate that institutional frameworks don't inevitably require months-long delays. Different choices are possible. Fifth, the ongoing opportunity. 3IATLAS hasn't left yet. December's close approach provides a second chance to get this right, to collect definitive data, to share it openly, to engage the community collaboratively, to demonstrate that lessons were learned from November's disappointments. The observations will answer key questions. Jet velocities will test sublimation models. Updated rotation measurements will constrain physical state. Detailed spectroscopy will nail down composition, including those elusive nickel ratios. High-resolution imaging will search for fragmentation. Mass loss rates will reveal activity levels. If this data flows into the community promptly, If NASA chooses transparency over caution, this time December could redeem November's failures. We could end up with the comprehensive, detailed understanding of 3IATLAS that the comet's scientific importance deserves. If institutional patterns repeat, if data remains siloed, if releases take months, if technical depth is sacrificed for public accessibility, then the disappointment will compound. The community's patience has limits. Continued underperformance will have consequences for NASA's credibility and support. Sixth, the role of amateur astronomy. One of the most striking aspects of the 3IATLAS story is how skilled amateur observers contributed meaningfully to scientific understanding, not as secondary sources confirming professional work, as primary documentarians capturing details that official channels missed or delayed sharing. This represents a democratization of astronomy that's been building for decades. As technology improves and costs fall, the gap between professional and amateur capabilities shrinks. We're approaching a point where, for certain kinds of observations, distributed amateur networks can match or exceed what any single institution achieves. That's not a threat to professional astronomy, it's an opportunity. Imagine if NASA embraced this reality. If they coordinated with amateur networks, shared data bidirectionally, and recognized that scientific progress no longer requires institutional gatekeeping, the combined capabilities would be formidable. But that requires institutional humility and cultural change. Acknowledging that 8-inch backyard telescopes sometimes capture better data than billion-dollar space missions isn't easy for large organizations. The 3IATLAS experience forces that acknowledgement, whether comfortable or not. Seventh, the bigger picture about interstellar objects. 3IATLAS is only the third such visitor we've confirmed. Our understanding of interstellar object populations, properties, and origins remains primitive. Every visitor teaches us something, and 3IATLAS has taught us that these objects can surprise us. They don't all behave identically. Oumuamua was bizarre tumbling, accelerating, showing no obvious comet activity yet experiencing non-gravitational forces. 2I Borisov was reassuringly normal, exactly what astronomers expected from an interstellar comet. 3IATLAS sits between clearly a comet, clearly natural, but displaying characteristics at the edge of typical behavior. What does this tell us about the diversity of planetary systems? About the range of conditions under which icy bodies form? About how billions of years of interstellar travel affects composition and structure? We're just beginning to gather the data needed to answer these questions. Future interstellar visitors will add to the picture. Survey telescopes are improving. The Vera Rubin Observatory, once fully operational, will detect interstellar objects much more frequently than current surveys. Within a decade, we might have dozens of confirmed visitors to study. That sample size will transform our understanding, but only if we learn from 3IATLAS how to study these visitors effectively, how to coordinate observations globally, how to share data rapidly, how to balance careful analysis with timely communication, how to engage amateur contributions productively. The lessons from this comet extend far beyond this particular object. Eighth, addressing the speculation directly. Yes, Avi Loeb has suggested the possibility that 3IATLAS might be technological. Yes, that hypothesis exists in published papers and widely read Medium articles. Yes, it generates headlines and public attention. Is there evidence supporting a technological hypothesis? No. Not in the sense of definitive observations that require artificial origin. Everything observed is consistent with natural processes, even if some features are unusual and not fully explained. Should the possibility be completely dismissed? That depends on your philosophy of science. If you believe we should only consider hypotheses after obtaining evidence that demands them, then technological origin should be off the table until we see something truly inexplicable. If you believe we should lay out all logically possible explanations and then systematically test them, then technological origin belongs on the list alongside natural alternatives to be eliminated or supported as evidence accumulates. Loeb advocates the latter approach. His argument isn't that 3IATLAS is definitely artificial, it's that we shouldn't reflexively dismiss the possibility without actually testing it. Measure jet velocities and composition to see if they match sublimation or require other explanations. Look for signals that technological objects might emit. Keep an open mind rather than assuming naturalness without verification. That's a defensible scientific position, even if most astronomers disagree with giving technological hypotheses serious consideration at this stage. Science works by testing ideas against evidence. As long as the tests are rigorous and the standards for acceptance are high, considering a wide range of hypotheses is reasonable. Where Loeb's approach generates controversy is in public communication. Raising the possibility of artificial origin, even carefully hedged with probabilities and caveats, inevitably generates headlines about alien probes, and Harvard scientist suggests extraterrestrial technology. That can overshadow the actual science and make other researchers reluctant to engage. But that's a communication challenge, not a scientific one. The tests Loeb proposes, measuring velocities, constraining composition, looking for signals, are exactly what good science should do, regardless of whether artificial origin is being considered. Those measurements advance understanding whether 3IATLAS turns out to be a perfectly normal comet or something more exotic. And here's something worth emphasizing. The reason Loeb's speculation gained traction is because NASA's presentation left too many questions unanswered. If the November briefing had provided detailed analysis of jet velocities, comprehensive spectroscopic results, thorough treatment of composition anomalies, and rigorous examination of the rotation versus collimation puzzle, there would be less ambiguity for speculation to exploit. Speculation thrives in data vacuums. NASA created a vacuum by under-delivering. Better communication and transparency would have filled that vacuum with solid science, leaving less room for exotic hypotheses to gain attention. Ninth, what this means for you, the viewer. If you've followed this investigation through 160,000 words across 2 videos, you clearly care about this topic. You want to understand what's actually happening with 3IATLAS. You're not satisfied with surface-level reassurances. You want the technical depth, the honest grappling with puzzles, the acknowledgement of what we know and what we don't. That makes you exactly the kind of engaged, curious person that science needs. Not just as a passive audience, but as active participants who demand transparency, ask hard questions, and push for the kind of rigorous analysis that advances understanding. Don't let institutions treat you as needing protection from complexity. You're capable of understanding uncertainty. You can handle admissions that some things are genuinely puzzling. You deserve detailed, technically rich information rather than simplified messaging designed for the least informed segment of the audience. Keep asking questions. Keep demanding better from institutions that spend public money to explore space on our behalf. Keep supporting the amateur astronomers whose open, collaborative approach often produces better science than secretive institutional processes. And keep watching the skies, because 3IATLAS is still out there, still observable, still teaching us about the universe beyond our solar system. The investigation continues through December and beyond. New data will arrive. New analyses will emerge. Our understanding will evolve. Finally, the fundamental question, was NASA's handling of 3IATLAS a failure? That depends on what you value. If you value public reassurance above all else, preventing sensationalism, maintaining institutional credibility, projecting competence, then maybe the November presentation succeeded. It prevented panic, emphasized safety, and presented confident conclusions. If you value scientific transparency, rapid data sharing, honest engagement with puzzles, and collaborative advancement of knowledge, then the handling fell short. The delays were too long. The analysis was too shallow. The communication was too managed. The opportunities for better science were partially lost. Most of us probably value both things: reassurance and transparency, confidence and honesty, accessibility and technical depth. The challenge is balancing these competing priorities. November's presentation leaned too heavily toward one side. December's observations provide a chance for better balance. Will NASA seize that chance? We'll find out soon. In the meantime, we continue watching. December 19th approaches. The closest approach to Earth happens in less than a month. Telescopes around the world prepare. Amateur networks coordinate. Professional observatories allocate time. Space telescopes plan observations. The data will come. The question is what we do with it. Whether we share it openly and analyze it collaboratively. Whether we engage with the puzzles honestly or gloss over them for the sake of clean messaging. Whether we let institutions gatekeep understanding or demand democratized access to the science. 3IATLAS came from another star billions of years ago. It traveled through cold interstellar space for longer than our solar system has existed. It's passing through our neighborhood for just a few months before departing forever. This is our one chance to learn what it can teach us about worlds we'll never visit and processes that happened before Earth formed. That opportunity is too precious to waste on institutional caution, communication management, and superficial analysis. We need the best science possible: open, honest, rigorous, collaborative, fast. December will show us whether we get that science, or whether the patterns that disappointed us in November repeat. But regardless of what institutions do, the community, professional astronomers, skilled amateurs, engaged observers, curious people around the world will keep investigating, keep questioning, keep demanding better, keep pushing toward understanding, because that's what science is, not institutions handing down conclusions, but people collectively grappling with mystery, testing ideas against evidence, correcting mistakes, building knowledge incrementally through honest inquiry. 3IATLAS reminds us that the universe still holds surprises, that we don't have everything figured out, that objects from other stars can challenge our assumptions and push the boundaries of our understanding. That's exciting. That's inspiring. That's why science matters. And that's why we'll keep watching, keep investigating, and keep demanding the transparent, rigorous science this remarkable visitor deserves. The investigation continues. 3IATLAS hasn't finished teaching us. December's observations will bring new data, new insights, new opportunities to understand this interstellar visitor. We'll be here, analysing everything that emerges, following the amateur networks that continue to outpace institutional releases, examining the spectroscopy when it finally appears, testing whether the December observations answer the questions November left hanging. If you want to stay informed as this story evolves, subscribe to this channel. Hit the notification bell. This isn't the last video on 3IATLAS, not by a long shot. As data flows in December, as analyses emerge, as our understanding sharpens, we'll be here breaking it down, examining it critically, and giving you the technical depth that official presentations too often lack. The community will be watching NASA closely. Will they learn from November's disappointments? Will the December data release demonstrate better transparency and speed? Will the analysis dig into the physics properly this time? We'll be monitoring all of it, comparing institutional timelines, examining whether amateur networks continue to lead professional releases, tracking whether the puzzles get resolved or deepened. Beyond 3IATLAS, this is about how science operates in the 21st century, about what we should expect from institutions funded to explore space on our behalf, about whether transparency or caution better serves scientific progress, about whether democratized astronomy through amateur networks represents the future, or whether institutional gatekeeping persists. These are big questions. 3IATLAS forces us to confront them, and the answers matter for every future discovery, every rare visitor, every opportunity to expand human knowledge. So stay engaged, keep asking questions, keep demanding better, keep supporting the people and networks doing excellent science, regardless of institutional affiliation. The comet is out there right now, moving through space, carrying its secrets. December 19th approaches. The optimal observation window opens soon. We're ready. The community is ready. The telescopes are ready. The question is whether the institutions are ready to match the moment with the science it deserves. We'll find out together. Clear skies, everyone. And keep watching 3IATLAS. This story is far from over.